We are ready to go live. It is time now. We are going to start. Kyle, is there any improvement in the quiz engagement score?
Just a few. There is a slight improvement.
Okay. Quiz number 4 is standing at a total of?
Right now, I think it's around 9 attempts, 9 or 11.
11 attempts. That's good. All right. Let's start now. So folks, we can start the recording.
Oh, yeah.
So today, we are going to do our labs on multilinear regression, regression in many variables. That is one of the topics for today. Besides that, we will also do univariate regression on a real-world data set, the old Faithful Geyser in the Yellowstone National Park in US. I'll give you guys a background on it. It is the Yellowstone National Park, and for those of you who are not familiar with it, which I think most of you are, but yeah, it is it's a geologically or geothermally active region. It's a volcanic, live volcanic sort of a lot of plate tectonic activities happen there. And there's always there's supposed to be the molten lava just sort of below the surface or about to erupt or something like that. It's very, very active region geothermally. One of the features of that region is that you have these geysers. Geysers are this water shooting out of the ground to great heights for some time. Think of it as a pressure cooker valve. When inside the water pressure is high, it just shoots out through these geysers. The geyser runs for some time, let's say about 20 minutes or 5 minutes or whatever it is. And after that, as the pressure releases itself, the geyser will quieten down and stay quiet for some duration, and then it will again erupt. The old Faithful Geyser gets its name from the fact that for many, many decades, it has been faithfully erupting every approximately an hour. It is within 40 minutes to 2 hours. It erupts. Now, the waiting time for the next eruption is dependent upon how long the previous eruption was. Sort of makes sense from a physicist perspective, physics perspective. If a geyser has been running for quite some time, a lot of pressure is released, and so it takes longer to build up pressure and the next eruption to happen. So in this data set, we'll have one predictor, which is the duration of the last eruption. And what you have to predict is how long you have to wait till the next one. The waiting time is the predictor for the next one. But the reason I bring it up is sort of univariate. We did a lot of very hard data sets. In real life data sets, I was somewhat simpler. And we are going to use this as an example of one of the data sets. So this is the old Faithful Geyser. If you're looking at my screen,
We can't.
or not yet?
No,
Not yet,
we can't see your screen.
And I think, did I remember to do the YouTube thing? Oh, yes. I did that YouTube thing. Okay. So let me share. That is it. Now, are we sharing the geyser picture on my screen?
Yep.
Yes.
So this is it. This is an artistic rendering of how the geyser is. You can see this water shooting off to great heights. One of the great features, and of course, in US, everybody knows about the Yellowstone National Park. It's one of the most magnificent national parks So worth visiting. So I will load this. So this notebook is actually now increase the font size and go, sorry, and go one more time. Okay, there you go. And there we go. So this data, is it readable now to everyone, guys, on your screens? Considering that we are a live streaming.
Could be made a little bit larger. Yeah.
Okay, there we go. So this data is very simple. We have eruptions. This is the duration of the eruption, I presume in minutes, and how long you have to wait for the next eruption. Those of you who are in California, you probably know that we have our old Faithful Geyser here also in Bay Area, in Calistoga, Napa, Calistoga area. It's very, very nice actually. Kids totally enjoy it if you have young kids to go to. So the eruptions, of course, are not as long. They take 3, 4, 5 minutes, and then you have to wait for some time for the next one. You can clearly see that if the eruptions are long, you have a longer time to wait. If eruptions are short, you have less than an hour to wait, right? So this is the nature of the data. Now, some of the best practices that we have been developing along the way, I will assume hereafter that we always do. One of the things we learned is it is a good idea to use a scalar of the data. And standard scalar is quite effective if you don't have outliers in the data. So you can verify that this data set doesn't have outliers. Actually, we'll see it in a moment. We scale the data. We look at its descriptions and so on and so forth, its eruption.
When to scale the data, like after doing initial analysis or just starting with the scaling?
No. You should always look at the histograms before deciding on the scalar. So here I have not done because, so this data set, do you notice that I have it here, right? I have not taken the time to do a lot of it's cyclic. I should have plotted this figure before doing the standardization. So what happened is that I knew I'm so familiar with this data. So I've done it sort of backwards. I standardized it, but I should probably have waited to do a data visualization before standardizing. So if you look at the data standardization, it will not change the shape of the picture. It will just change the XY axis. So because I standardized the data, you notice that the mean is around 0. It is not very clear, but the standard deviation is 1, and it will show up in a little bit. So what do you notice? That there is one cluster of values here and one cluster of values here, right? So you have either short bursts or long bursts of the old Faithful Geyser. It erupts pretty much two groups of eruptions, short and long. If you notice that, and you can see it once you standardize the data, what do you expect the mean to be? 0. And so it is 5.15 into 10 to the minus 16. Practically, that's the definition of 0, because in floating points, it's almost never do you get 0. Standard deviation up to 2 decimal place at least is 1, right? So the data has been standardized. There are no null values in the data. If you plot it, it looks like this. You can see 2 groups. So later on, when you learn about clustering, we will do clustering on this data too, right? So you'll get 2 clusters, one for short eruptions and one for long eruptions. Then today, I'd like to introduce this very useful plot. These are called the pair plots. The 2 variables, eruption and weighting. What it happens is this is pretty much the histogram that we were looking at, except that the word for that is called kernel density plots, kernel density estimator plots. What it means is, I'll give you an intuition of it. Kernel densities and kernels are things we will cover in great detail when we do the neighborhood methods. The word kernel is very central actually to a lot of things we'll do. But since we haven't done that,
is that a kernel function or
it is the same thing. It is so this is the intuition I'm giving. The intuition is if it wasn't just this few hundred rows of data, what if the data was asymptotically infinite? Then what would be the distribution that you would see? Density estimation, density distribution. So kernel density estimation is essentially that intuition. It estimates that distribution function, which would have been there, assuming that the data set was very, very large. How the histogram would have looked. Histogram would have looked like this, right? So with finite data, it is an estimation of that. It's a continuous curve. That's why it's called kernel density, a probability function that estimates or sort of how much that will be.
So how does it extrapolate? Some ways it's trying to extrapolate, right?
Yes, it does. And we'll learn about that. What happens is the kernel here, typically these are Gaussian kernels. How do you fit these and put them together? We'll learn about it in the neighborhood methods will do. But while that topic will come, it's not that hard. See, you notice that this picture here, right?
Yes.
You can see in the two-dimensional variable, in the two-dimensional space, the contour plots.
Right.
Of equal density. So this is it. It's a beautiful concept. At this moment, I thought whether to introduce or not, and I thought I'll introduce it because it's just such an important visualization. It's good to introduce it early. Right? The top right hand is, of course, the scatter plot. We are all familiar with. This is the wait time, eruption time. As you can see, they are bimodal distributions: short, long, short, long. So. And when you look at the contour plots, you can literally see the two clusters form here. So it gives you an insight into the data. Now let's build a regression model where eruptions, like how long did this eruption last, and is the predictor, and the target variable is how long do I need to wait? If I've seen an eruption of 5 minutes or 4 minutes, now how long should I wait? By the way, it's really very, when you take your children, for example, here to Calistoga, the first thing your kids will do is they will watch with great excitement, they'll watch the eruption. And then the very next question they'll ask you is, okay, when do I get to see the next one? Right? So, well, this is going to answer exactly that question. So by now you should be familiar with it. We built a linear regression model.
So a question.
Yes.
Is the other way also the thing holds true? Like if I wait for this long, can I predict like how it will go, right? So,
yes, of course.
So y and x and x and y, right?
How long the next that is a good thing. Why don't you do that? But I think people haven't gathered the data this way, that if I see the eruption, if I wait certain time, how long is the next eruption? I don't know whether this data is sequential. If it is, then you can use it. You'll have to look into the original source of the data. If that is true, then that could be another good analysis to do. It's a good idea.
Like it's a time series kind of thing to
it. Right, yeah.
Not just looking over time, but
yeah. So look into the source of the data, whether it's sequentially given or not. So building a regression model, by now, guys, you would all agree that this line of code is pretty easy and straightforward for you to get. On this big screen, is it coming out legible from the back row? Premjit, are you able to see the code clearly?
I'm looking at my computer.
Oh, you guys are looking at your computer. Okay, yes, good. But on this monitor, is it big enough, or do I need a bigger monitor?
No, you have to make it bigger.
I do need to make it bigger. Okay. What about now?
Now this is perfect. Yeah.
This is perfect. Okay. So look at the screen then, so that I can see your faces. Here we go. So this model, I hope you would agree, is straightforward. Then we build a prediction model. By now, this is also very. So one new thing I wanted to tell you. See, whenever you're predicting, typically we look at mean squared error, which is good, but sometimes the root mean squared error is more intuitive, right? So suppose somebody says that the house price was 4,000 and your root mean squared error is 100. You know, this pretty accurate estimation of the house price, right? So that way it is good to know what the root mean squared error is. So, and the way you do that, root mean squared, is set squared is equal to false. If you set squared is equal to false in the mean squared error function, it will get that. So let's look at the residual analysis. What do you say, guys? In the residuals, do you find any choice? Do you see homoscedasticity or heteroscedasticity? Homoscedasticity, isn't it? You don't see the variance of the residuals change as you move from left to right, right? Move along the x-axis. So there is a rough homoscedasticity. So this looks encouraging. What about the distribution of the errors? Is there any skew in the distribution of the residuals on the side? No pronounced skew, right? Very modest, if any, skew. And you can do that by computing the skew, but I'll leave you to visually just inspect and say, yes, there isn't much skew. So let us now, what is the final thing we do? We visualize the model predictions, isn't it? Especially with one-dimensional data, it's easy to do. So there we go. And these are your predictions. So is this a good model? It is. I leave a homework for you. And what is the R squared, by the way, that we got? Do we remember? 76%. 76% is it good or bad?
Okay.
Yeah. When you look at the data, you have to tone your expectations. The data is like this. So there are things that you don't know, right? The geothermal activity, which are actually contributing to it, and you have no access to those variables. So this is the best you can do with this. So it's a pretty good model, and you can verify that. Try building and these things, I don't know, guys, take this homework seriously, because when you do that, a polynomial regression, you have the code, you can try it out in 5 minutes. Try it out, see, does it give you a better model? And then ask yourself, should it give you a better model? Right? So leave that as an exercise for you. So this is the old Faithful Geyser.
So I see one quick question here.
Yeah.
So there's also another possibility that happens. Yeah, let's hold that visual.
Yeah.
So I'm projecting a little from this visual to frame my question. There's a possibility that there is a structural change in the data, right? For a moment, let's assume the lower cluster had a different gradient compared to the higher cluster. If you had to fit a single line through them.
Yes, very good question.
Bad, but if you fit two separate single lines,
that is right.
They would be good.
That is right.
We haven't discussed an inference
We
on
haven't
how to find that and how to treat that.
Yeah. So the thing is, when you do polynomial, because it gives you the ability to flex, it can actually come up with different slopes in different regions. Try doing that. But more
a single polynomial will actually fit it reasonably well.
Yeah, it will do.
As
but there
opposed
is
to identifying a split in the data and saying,
yeah,
let's fit two linear models.
Yes. And then you have to join the two somewhere in between somehow. So those are called, and we will come to, remember I said that the word kernel is an advanced topic we'll do later. Those are called kernel-based regression models. That's what they do. That's one way of doing it. Another is to do something called spline. Make local linear models and keep joining them. There is yet another way of doing it, which also we will do, again to do with kernel methods. It is called kernel nearest neighbor, and there are methods like LOES. What you do is you look at local regions and you make tiny regression models in little patches, and then you stitch those patches together. When the data is highly nonlinear, that is effective. In fact, that old technique is called LOES. In geology, that was very, very often used. The word LOES comes from there.
Okay.
Right, sir. So there are many, many techniques we learn. Remember, this is the beginning of machine learning. We have another 8 months to go.
Right. So like two comments on this observation. It reminds me of zero data, housing data, right? Like actual sales and things like that, which had that characteristics, like at different price ranges, you would have different factors cause the to change, and you could clearly see the distribution.
Distributions.
The few $1 million houses, it was cool, nothing mattered. It basically how far you were away from the whole neighborhood. Versus with the lower ones, you could clearly see like number of bedrooms, those kind of things. matter that over there, there's completely different factors. And
They're structurally different.
They're structurally
and you
different.
see those gaps
Yeah.
between one price range
Yeah.
to the other.
Yeah.
So that was.
No, this is a very good point you brought. Let me further elaborate. For those of you who are remote, Sachin brought up the point that the Zillow housing data shows pronounced non-linearities, and different regions of the feature space, there are different kinds of activities or factors involved. This actually goes to the heart of machine learning. One of the things we will learn is real life is highly nonlinear. And so most good predictive models, they are telling very different stories in different parts of the feature space. So the models are nonlinear. And so when you ask which features matter, like people often say, if house, what determines house price? There is never one answer. The answer depends upon which price range, which geography, which part of the feature space are you looking at? Because there are different factors in play in different, and people know that. People who are in real estate, they will tell you that real estate is a very local market. The forces are very local. That is why local real estate, there's no one global real estate company that has the answer to all problems, right? Or has perfect. They're all based on local real estate intuition. And it's the nature of it. In diseases, everywhere it's true. For example, when you look at diabetes, if you ask in children, pediatrics, or up to age 15, what is the most common cause of diabetes? Those factors are completely different for what is most common cause of diabetes in people over 40, right? Mm-hmm. So the game changes. So even though we build one model, one of the answers to this question, why are most models non-linear, effective models non-linear? Because you need non-linearity to capture the fact that there are different realities in different parts of the feature space, right? And that's a big topic. In fact, that's where we are heading. In another 2 weeks, we are still in the linear world. In 2-3 weeks, 4 weeks actually, we'll be completely in the non-linear world, right? We have a lot of things to do: kernel methods, support vector machines, ensemble methods, boosting, bagging, forests, right? There is a, and then of course the neighborhood methods. There is a lot that we are going to do, but that will come in due course of time. But the good thing is, the old Faithful Geyser I like, because it's a very neat, clean data set. It has a nice story to tell and very easy to analyze, isn't it?
There's another data set which reminded me to take a look at, is basically the fat, the correlation between the fat and the waist size. And what happens is that every waist size, so there is, as the waist size increases, the percentage of fat also increases. Mm-hmm. But there is a distribution at each one of them has its own maxima and minimum. So okay. There is a distribution of people like certain waist sizes, how much they spread. Okay. So that distribution itself has a nice, what you call, patterns in the distribution itself. Okay. So as people tend to have bigger waist, the fat side of it starts to dominate. Okay. Versus the thinner waist, the distribution of fat, it basically becomes like pretty normal. Yes. In the sense that it's muscle, and so it's a very interesting data set. I can speak from personal experience. All right, guys. So with that,
so if you look at just the visualization of this data set.
Yes.
If we not this here, the other one.
At the end.
Yeah, so if you look at the way the distribution is, and if you also look at the residual plot, it kind of, even though residual looks random, yeah, but from the distribution perspective, it is mostly similar.
Yes. That's right. I mean, you can imagine these little residuals falling off this, and you can see that that is what the other plot is showing. Yes.
Yeah, so that's why I think you're doing this the polynomial regression.
Yeah. So try this out. So guys, now that we have the geyser, remember that here, life was very simple. How did we build the model? Building the model for us was model.fit, linear regressor, regression model.fit. So this is, we are using a library, scikit-learn library. And in real life, you often use libraries, but then it is also true that you need to learn how to do without libraries. Just from first principles, how would you do the learning? We learned all this theory about gradient descent and so on and so forth. So what does it mean for us to do this by hand? So we are going to do the same data set, simple Geyser data set, but this time around, we will use gradient descent, right? So I do the basic stuff here, things that you're familiar with. Here, the same data set, I use it, scale it, and so on and so forth. The same eruptions, mean is 0, standard deviation is close to 1. Guys, do you see it? Yeah. Right. And now,
Yes, yes.
one of the things that I do is, so these little tricks, you'll see me continuously introduce little tricks here. Yeah. What happened? This table became, do you see that this pandas table, data frame table, now looks a little bit more interactive? Did you see the difference, guys, compared to this? Yeah. I put some color here and so forth. So that you can do by adding a style. I've added a little bit of CSS style to this table. How I've done it, you can see, and I'll leave that as an exercise for you to go and look at Support Vector's common notebook, how you can do styles. Of course, you should have your own styles. My style, I prefer these colors, which are off colors. Typical corporate styles are blue, but I spend my whole day in corporate world, and all I look at is blue, different shades of blue. So I don't feel like looking at that anymore. So I've made all of Support Vector colors anything but blue. Well, there is blue, but this blue is midnight blue. It's supposed to be in the color spectrum compatible with it. So, well, okay, here it is. Mostly reddish. I like salmon color. This is the scatter plot of that you're familiar with. This is the eruptions waiting time. Again, you're familiar with. This is just a recap. So now let's go to gradient descent. The beta, next value of the parameter is the beta's current value times this. Right? This is it. This is just a recap. We will just take the simple unregularized regression, a simple linear regression, sum squared error is enough. Then if you just work out, it is sum squared error. When you take the gradient of the loss function, which is this with each of the parameters, if you work it out, you can see that it works out to this. Almost literally from here to here, you can see it if you're good with your calculus. Immediately you see it. Right? Do you agree that the partial derivatives with respect to beta naught and beta 1 come to these two things? I'll give you a few seconds to absorb it and agree that that's obvious. Do you see that, guys?
Yes.
That's right. So we move forward. And so when you plug it into these values into the equation here, this equation, what it leads to is this. Beta naught. All we need to do now is to run the gradient descent. Now, gradient descent, we will start with the learning rate, which is very small. Actually, here I read 10 to the -5, but that becomes too slow a learning, too small learning in a single step. I wanted it to be a little bit faster, so I made it 10 to the -4 here. Also, typically beta naught, beta 1, you start with some random value. So what you should do is remove my 4 - 4 and start with some random values. When you start with some random values, then it will gradient descent. Now, for reasons of data visualization, because you will see a plot that I visualize here, I have deliberately started in such a way that the plot that it will draw will bring the intuition out for you. So I deliberately forced it to start at this point, but for no rhyme or reason, just for visualization perspective. Now we need to discuss a concept called epoch. In machine learning, during the learning phase, we define an epoch is one journey through the complete data set. Are we together? When you have visited every point in the data set, right? You have completed an epoch. Now in the gradient descent step, if you look, do you notice that we sum over every single point at each step? If you look at this, look at this, we sum over every point when we do the next step. So what does it mean? At each step, we complete an epoch.
For the training data.
In the training data, yeah. Because in each step we are computing the gradient by summing over the errors of each of the residuals of each of the data points. Therefore, one step of gradient descent is one epoch. Now, there are many kinds of gradient descent. What I've been calling gradient descent in the more formal language would be called batch gradient descent. A batch gradient descent is a descent in which the entire data set is one batch. The opposite of that is stochastic gradient descent. In stochastic gradient descent, one step is just one data point. You don't have a summation here. Summation is missing. You just learn from one point and its mistakes. And then there is a method in between that doesn't do, these two are extremes, to take the entire data set or learn from one step. Learning is from only one point. The alternative is to learn from small batches of points. Those are called mini batch. So suppose you have 300 points, you will create mini batches of, let's say, 16 points each, right? And then your each step will compute the loss from 16 points. Next step will compute the loss from 16 points, and it will learn from that. So there's a lot of learning by the time you run through the whole epoch, right? Approximately 20 steps you would have taken to learn through about 300, maybe 19 steps you would have taken to learn through those 300 odd points, right? If your mini batch size is 16. So there are many different variants to gradient descent. The one that we will look at here is the very simple one. We sum over all the points, right? It is the so-called batch gradient descent, full batch. Now, this word is a little bit abused. The technical distinctions are batch, stochastic, and mini batch. But a lot of people, because of colloquialism, they will call mini batches batch gradient descent, especially in the deep learning community, and it becomes rather confusing sometimes. But remember, these are the correct terminology. So now, whatever we wrote here, I will rewrite it in code. So I said alpha will be very small. I'm starting alpha as, what does this line possibly say? Alpha is equal to power 10 minus 4. What do you think it does?
10 to the power minus 4.
Exactly, thank you. So it is alpha is 10 to the minus 4. Then beta 0, beta 1 are the two parameters of a line, remember? Slope and intercept. I could take initial value to be any random thing, but I have deliberately taken 4. That is purely for visualization purpose. You should change this code. Your homework is to remove it and just actually initialize it randomly. Epochs is 200. What does 200 say? We are going to take about 200 steps. Why? Because simple data set, 200 is already enough, right? It's a stopping criteria. You learn for 200 steps and stop. Now you break the data up into X and Y, which of course is straightforward. You break it up into the arrays. And then what are the values that you have to learn? So alpha is this, beta naught, beta 1 is this. We are going to learn 200, epochs. Now what do I do? And this is the heart of it. This is the inner core of what we are going to do with the gradient descent. The first one, I just create a data frame in which at each epoch, I will store that whatever the value of beta naught, beta 1 we have learned so far, I'll store those, and I'll store the value of the loss function. Like what is the loss function? So what should happen as I go from epoch to epoch? I should see an improvement in the value of beta towards the final answer, betas, and I should see a decrease in the loss, isn't it? You wouldn't expect to see increase of the loss function, blowing it up. You should see a decrease of the loss function, isn't it? Because after all, our loss surface is parabolic, isn't it? So it should see a decrease in the loss function. So let us now please pay attention to this loop. It is the crucial loop. For each epoch, and the number of epochs, so for 200 epochs, what do? Let's look at this step and tell me if it looks confusing. Compute the gradients. Here are the gradients. So you notice that this is sum over yi minus beta naught minus beta 1 times xi, right? Is this now, compare this to this statement. Beta naught, the next step of beta naught is this, beta naught plus alpha Right? So no, first the gradient. This is the gradient. Gradient is equal to minus the sum of yi minus beta I minus beta 1, beta naught minus beta 1x. Please pay attention to this equation here. Is this exactly what I have written in code here? Go ahead. Somebody has a question.
So it's yi minus yi hat the whole square, right? So
Yes, pretty
when
much.
we differentiate it, shouldn't there be a 2 in front, multiple of?
Yeah, I sort of, the last, yes, that is a very good point. I sort of glossed over the constants, right? The point
Okay.
is 2, there should be a 2 here, but I have glossed over the constants. Right. So
Okay.
if you want to be very precise, we can change our loss function. Where is it? Least square is equal to sum over. So let me just make it like this. Frac 1 over 2 is equal to, once again, this frac. Okay. So let us be precise. People, when they're explaining, they tend to gloss over it. But why gloss over it? Okay, now are you feeling better? Look at this. I added a half here. So then when you take the gradient, that there won't be a 2 here.
Okay. Yeah.
You know,
okay.
These constants, 1 over n, 1 over 2, these things, people tend to gloss, or in the gradient, you can apply a 2, but it won't affect the results, basically.
Okay. Okay.
That is why you gloss over these things. But it is a good point, good that you caught it. So compute the gradient. So we now have the gradient. Do you notice that this looks exactly what you thought? Minus sum over yi minus beta naught I minus beta 1 x1 xi. Does this look intuitive, guys? Anybody? Does it feel intuitive, this statement, in view of this statement here? Look at this. Minus sum over this quantity.
Yes.
Right? And if you're not understanding it, let me know, because I have written it in such a way that the code is almost identical to the math. Yeah. Likewise, the partial derivative with respect to beta 1, d beta here, I mean, gradient of the loss with respect to beta naught. Right?
One Python question.
Yeah.
Zip will tell us if x and y, the cardinality was different, right? It basically makes a Cartesian pair of.
Yes. Yeah. Basically, zips is like a zipper. You know, one from this side, one from this side, one from.
And if the cardinality was different, it will go down.
It will give you. I don't know whether it will throw an error. I think it will stop at the shorter one. But check it out. It's a good question. I mean, the best thing is to do a tiny experiment and see what happens. So there we go. Now, the next step is, once you have, look at this equation. Once we have the gradients, you can take the gradient descent step. This is the gradient descent step, right? So let's go take the gradient descent step. Here it is. The gradient descent step beta naught is beta, next value is beta naught's current value minus alpha times gradient of the loss. Like this equation, guys, I hope this is pretty self-evident, right? This is literally the definition of the gradient descent, isn't it?
Yeah.
So this is it. And then after that, what do we do? Now that we have new values for beta naught and beta 1, we can go compute the new loss. What is the loss now that we have improved values of beta naught, beta 1? Okay. What is the loss here? And we store all of it in a table. This intermediate values table, which we can see what it is. By the way, whenever you have a table to display with floating points, it can be very annoying. You can get values till 5, 6, 7, 8 decimal points, and it becomes messy. So it is a good idea to contain the precision, limit the precision to a sensible value. 3 digits is more than enough for us to do. So I put the precision here for 3 digits. So it's your choice. You can make it 2, 4, whatever it is. Now, do you notice that beta naught starts out with close to 4, but then it gravitates towards 0. isn't it? Do you notice that beta naught gravitates to close to 0 and beta 1 gravitates to 0.9 according to our learning? Now, what did scikit-learn have to say? Let's go and see what did scikit-learn have to say when we did that. Do you remember what was the parameter? What was the beta naught, beta 1 we found? Look at this. Does it agree with us? Beta naught, is it pretty much? Beta naught here is 0.012. And what we found is beta naught is 0.016. If we had run it for another few hundred epochs, it would have converged there, right? And slope is 0.9168. And what are we getting? Slope is 0.913. Means I stopped at 200 epoch. I'll give you a thing, guys. Run it for 400 epoch. See if the two answers begin to match. But do you notice how easy it is that you can do the gradient descent, quite literally the inner workings by hand? You don't need to use a library. And as I said, it's good to develop this practice because as you get to more advanced topics, you will be doing it by hand. So let us here plot this. Do you notice that the beta naught values gravitate to its final answer from 4? Beta 1 also gravitates to its final answer. What is the final answer for beta naught? It is, what do you see here, guys, in the graph? Beta naught's final answer is
0,
close
around
to,
0.
and beta 1's final answer is this thing, close to 0.9.
Yeah.
Right. This is it, as you expect. What about the loss function? Learning is proper only when you see the loss function go down. But what if it starts going back up? You're in trouble, right? Or some strange thing happens, you're in trouble. So here, is the loss function going down steadily? Yes. No. So here I took alpha is equal to 10 to the minus 4. What do you think would have happened if I took alpha is equal to 1? I will leave that. Big steps of learning. I'll leave that as an exercise for you to figure out. Right? I mean, we can run it right now. If you guys have downloaded the code, you can run it right now and see what happens. But I want you to do it yourself and see what happens. Now I'll plot the contour surfaces. Remember, I told you that in the parameter space, in the hypothesis space, the error bowl, this error bowl is projecting down to the hypothesis, beta naught, beta 1 space, parameter space, right? Or what I keep calling the hypothesis space. And there, what will be the projection of these the equal error curves here? They will be curves on this hypothesis space, isn't it? Right? So those curves are called contour plots, right? Or contour surfaces. In the contour plot, you see these lines. Of course, because we are dealing with a 2 dimensions, so these are lines. More broadly, they will be curves. There'll be surfaces. So these are the contour surfaces on this plane, right? So I've drawn it out. All those. This is real, by the way. This is actually coming from the calculation we just did. Here.
And see, in terms of the colors, did you link that to some parameter for those colors to happen like that?
Yeah. So what you do is you typically pick a good color scheme. Viridis is the default one, I believe. The closer you are in Viridis, right, the more reddish or violet, or is it violet, or what color would you call the center? Violet, right? Violet, purple, whatever. And the outer you go, it goes through blue, green, finally yellow. Right. So high values are yellow. And I have put the values also. Do you see that 100, 200, 400, 800, 1600? Yeah. Now you notice that it pretty much the error reaches the minimum error. Now, what is the minimum error we reach? Look at this. At 200 epochs, we are close to what is the error table showing? 52, approximately 51.3. Right? That is where the minima is achieved. And you can see that the minima is achieved pretty soon, right? But there is a little bit more learning to do. You know, if you really look at it, the curve is still going down. So you can run another couple of hundred epochs and get the near perfect answer. But this is good enough for us. this is it, because I wrote the code in such a way that it will run on all your laptops. It shouldn't be that your laptop hangs and you have to go out for dinner before you can continue. So now
We keep the alpha constant here.
we
Is
keep
it?
the learning rate constant here. That is right. That is an important point. We keep the learning rate constant, which is not true when we do much more complex regressions or complex classifications and so forth. You will see that what you do with learning is a whole subject in its own right. Is like a specialized bit of research in its own right. They're very interesting and fascinating things people do on how they change the learning rate as you learn, right? And there's a lot going on there. There's all sorts of things like one-shot learning and this and that. And we'll talk about it when we get to the deep learning world. And now remember, I keep talking of the bowl. Physically, my error surface bowl. How does it look in code? How does it look for the same Geyser data set? I visualize the code for you, right? So what happens is, remember, we started at 4.4. We start here, and the learning happens with this point. You see the loss point going down, 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 down to the bottom of the bowl, and its projection on the hypothesis plane. Do you see these points? And in the beginning, do you see that the loss is decreasing by big amounts? I deliberately put points to show that it is like a rabbit that's hopping forward, big strides. And then the strides become slow. It starts creeping. The little rabbit turns into a tortoise, right? It's creeping forward towards the final answer, right? And the code is a little bit more involved. I mean, it needs understanding. There's nothing machine learning about it, but usually in this world, you'll realize that once you get the hang of machine learning, you'll start finding that you need to master data visualization, which is a subject in its own right. And believe it or not, like you may dismiss it and say, hey, that's not intellectually challenging. Actually, it is. You know why? Because a good typical data scientist make, I don't know, I'm giving you current figures in the Silicon Valley. Outer box 250. If you're also a data engineer and a data scientist and you're a full package, well, outer box $500,000 a year. If you are a data scientist and data engineer and a complete beautiful visualization guru, I happen to know from personal experience from some people who are doing it. Can you guess where do they fall? 200, 300, 400? The outer box of com. Easily 3-4 million.
3-4 million.
So what I'm trying to say is that, guys, never underestimate the value of good visualization or beauty. In this field, right, mathematicians, it matters, right? So one way that I say it jocularly, don't take it too seriously. See, kids, when they play with crayon, right, we consider it normal. But as adults, we are not supposed to play with colors, isn't it? The only profession that lets you play with colors is, guess what? It is mathematics, isn't it? This is the only one where you see me writing in colored crayons on the blackboard. If you're physically here, writing in color, and on the digital blackboard here, and in the visualization, you can use a lot of colors judiciously. So guys, the visualization is profound. It can help make huge business decisions. I have seen it in reality. Florence Nightingale essentially founded the profession of nursing with one visualization from the of fatalities in the Crimean War, right? And that tradition has continued. When we say that a picture is worth 1,000 words, it's really true in the world of data, even more true, because when you create models and you come up with insights, and if you can visualize that insight, it is worth 1,000 words, right?
So why don't you use this during your talk when you actually teach this concept, the drawing part that you have done?
No, because then I can't do dynamically, right? I can't draw the surface and draw lines,
No,
etc.
but you can take this and then draw on this,
Yes,
right?
I could have done that. I could have. I tend not to use pre-prepared material because I feel that learning should be spontaneous and it should be in the flow of conversation. So to preserve, it's a basic educational philosophy for me. So to keep it in the flow of things, see, I have seen a lot of material and all that material is dazzling and I can create dazzling material. The trouble with dazzling material is we get dazzled. Whereas learning takes place best in the flow of conversation with almost no devices. Right. So when your younger brother says, explain something to me over a dinner table, you may at most have a pencil and paper in hand. But that explanation is gold compared to watching elaborate presentations on the internet. So that was one of the great insights. For example, Salman Khan. Before that, online education was all about well choreographed videos. I mean, it was almost becoming like Hollywood. If you go back and look at some of the Linda Learning or LinkedIn Learning now, or India Bayou, right? They are very successful. There's no doubt about it. But it's a different educational philosophy. There, each of the videos there is a subject matter expert who tells you what to say. Right? There is actually a choreography team there. There is an actor who will voice over, the instructor, who will literally master that script. And is not a subject matter expert, but will explain using the words the subject matter is given. And usually the person who's teaching, for example, if you go to biosector, is generally young and pleasing looking, making just the right gesticulations, right? So the entire thing is very choreographed. But the trouble is you can't ask a question in between. Isn't it? But Khan took the opposite approach, Salman Khan. He was just going to teach his niece. Right? So he just took a little board and scribbled on it and started explaining that. And that turned out to be perhaps the most profound revolution in education of this century. It completely rewrote how online learning should be done. Right? And you can see the effects of that everywhere. Before that, people used to do a lot of PowerPoints and so forth. But for example, if you look at Andrew Ng today, even he does that. Occasionally, he will come up with formulas, but then he will doodle a lot all over it in the Khan Academies, in the Salman Khan style. Right? Now, I have thought about bringing that. One reason I don't bring even like Andrew Ng some things written is because I feel that it forces me into a structure and it prevents students from driving the conversation. Whereas when I'm in the classroom, I would rather that the students' understanding or lack of it, the interruptions, the questions drive the agenda. In other words, don't come up with what you have to teach in a rigid form. Let the questions in the class create a flow of conversations and go with that, which is why I never really know what I will teach and how much I will teach or where I will put depth in. Yeah, so that freedom I have.
This curve, I remember I kind of plotted this like 5-6 years back using the primitive, whatever software was available that time. And it took me a hard time. I think I spent probably upwards of a week trying to get it running, right? But the part was the amount of detail that you have put in this piece drives the home
so well,
the thing so fast. Because I was planning to do this exactly like my whole, like last week I've been thinking of how to do it, and now you've just shown it over here. And I didn't know if during the class, if we had done that, if others would have appreciated or they would have got lost in just the beauty of this.
That is it. See, one of the things we realize in research is education is a very active area and a lot of opinions and so forth. And obviously, I'm not an expert in education. My understanding of education is through 30 years of teaching postgraduates, right? And 32 years now. But and you learn a thing or two, and I read a lot of books on education and research on education. But I'm not a formal expert in it. I'm an engineer and a scientist, physicist, right? But my general experience has been, and the body of research that I have read says, that two things you should avoid in education. Whenever you're doing online or something, keep your face away from it, right? Because human beings, the whole brain structure is designed in such a way that the moment it sees a face, especially the eyes, it latches onto that. And it just keeps looking. So remember, there were some videos which was using called light box. The guy would stand and write. It would look as though the person is writing on a glass from behind the glass, and you see the person. lot of videos where it is super impressive. But if you actually look at what people are paying attention to, they're paying attention to this guy speaking.
Through the
Through this, because our human mind is deeply conditioned to look at faces. That's how we recognize danger. That's how we recognize emotion. We keep looking at faces. So the best way to teach actually is to take the face away. Like, for example, when I'm teaching, I'm hoping, I don't know what you guys are seeing. What you're looking at is the code. And maybe in the top right-hand corner is my face somewhere, but it's not dominant there, right? The second thing that you learn is that use colors judiciously. Principle of least ink. Use color, but use the least ink to express it. When you see this, how much ink there is. Right? So it looks very pretty. Sometimes it's good. Like, for example, I believe that once you have seen those drawings, then to see this is very impressive. But to start with this, in my view, is not a good idea. It's a better way to first do hand drawings and then finally come to this. And not only come to this. So this, and by the way, the code, if you want to see, is very simple. What I have done is I've plotted the surface, right? Surface plot. And what I have done is, because see, here the loss is only 53. So the error surface is practically sitting on the parameter space. The net residual is too small. So just to visualize, I lifted it up. I deliberately added 2000 extra error points to it to create the visualization. Then you play around with alpha, but then there is nothing else. Now the contour lines, these are the hand-driven contour, making sure that my contour lines should be at these values. And then the rest of it is very simple. The contour plot and the main plot. This is it. 2-3 lines of code, and then you get it. It takes a little while to become good at plotting and 3D visualization, what you do. But then what you can do is, I've also given you, because I knew that some of you would want to do this on your own. So I've not only put the code, I gave you the code to make it into a movie. Right? So this code will make it into a movie with 1 point. Remember, I've set iteration to 0 for safety. If you blindly run this notebook, you may accidentally end up running this bit of code. So to prevent it from being done, I've set the iterations to 0. Comment this out and uncomment the next line out. Because when it runs on your laptop, unless you have a powerful laptop, it can easily run for a few hours. Making movies is always longer. Right? So ultimately, it produces this movie. Let's try this. Right? I will start this. I will just decrease the, just forgive me. So guys, pay attention. I'm going to start this gradient descent spread. Keep your eyes on this point. Do you see where my mouse is? Keep your eyes there and see what happens. Do you see the gradient descent taking place? Yeah. Right? And do you notice that as you come closer to the final, because at the bottom of the bowl, what happens? It's not steep. The gradient is low. Yes. So for a fixed learning rate, if the gradient is low, the steps you are taking are slow. Right? So you go like a rabbit and then you start creeping like a turtle, like a tortoise, towards the final answer. And there you are. Was it fun? Yeah. Right.
Yeah. So we have to re-download that lab.
Oh, yes, you have to re-download the lab. It is online though. Yeah, the latest version is there. Yeah.
What's the difference?
Come again?
Why should we re-download?
Oh, no, because my teaching faculty, we reviewed this yesterday or day before, so they didn't have the latest version. They didn't have the movie there. Oh, okay. This little movie was there.
That now. I downloaded it.
Yeah. Yes. So this is it. So guys, do you see that the magic behind the theory that I taught you, right, is very real. You can literally code that theory and see it work, right? And so that is that. That is one notebook. Let's take a 5 minutes break, and then we'll go to the next data set, which is about pondering over the mysteries of whether high horsepower engine have low mileage or high mileage.
Can you just go where you added the formula? I think it's the formula with half. Can you show the code?
Yeah, here is the loss.
Yeah.
Right. So, I have been sloppy with
like the latex
code. The LaTeX code. Oh, just double click on it and you'll see it. Frac half. You will get, I'll post this latest notebook also. Right? See, guys, whenever I do this, this is an old physicist style. You know what physicists do when they deal with equations? They set all the constants, they erase all the constants. So, you know, you can always tell a person is not a theoretical physicist because the normal physicist and everybody else will say E is equal to mc square. What will a theoretical physicist say? Can you guess? E is m. So all the constants are equal to 1, right? So for us, half, this, that, proportionality constants, they all disappear, right? Because it helps you reason if you just get sloppy with your constants. So in fact, most theoretical physicists books, that's literally the way they write it. E is equal to m. You'll never see E is equal to mc square. My professor, researcher, he used to put it very humorously. He says, what is a constant between friends, right? Or if you got the minus sign wrong, you would say, what is a minus sign between friends? So, all right, guys. So a quick 5-minute break, bio break. Let us regroup in, not 5, let's make it 10 minutes. Let's regroup in 10 minutes. I need to increase the price. How about now? Much better, right? This screen cost. The next biggest screen is 100-inch. This is 86 inch. The next biggest screen is 100-inch, which costs 70,000. I can't, unless you guys are all willing to pay 5x of TV. Have you got any early decisions? I'm doing early action for this of course, no, it's not decision action. Non-binary. Yeah, so I mean, I'm just Washington, University of Washington, everything else is ready. Again, every decision. No, not binary. I was thinking of asking for it, but I don't know. Like, we didn't something. Yeah. Yeah. Yeah, no, that's fine. I was, I'm still most of these colleges at a max state 3, and then I'm being educated in
No, this is the text package. What is it?
No, 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 I was just saying, step this way. You're telling us, right? Is this fine? Yes. And this is sort of the foundation you've missed. So you should be equal. Okay.
Because of the transformers.
It's still there, but it's sort of de-emphasized in view of the visual transformers. And there is more of computer vision itself. For example, I did teach you things like except and ransack. The foundation of computer vision. So I did teach you
What time?
It will literally be practically a brand new class because so much has changed in just like less than a year.
Play with these. Not still getting back to browsing through the notebook is not full.
Yeah. Yeah, actually, see, I give you all of this in a standardized situation. If you search in the internet, information is there, maybe in some cases, somebody would have done something. They would have written a medium out, and quite often you will read it, you usually see more in the yeah, but except for proportionality concerns, I think a lot of pains to make sure it works.
So there's a parallel thought running in my mind. Thanks to the Julia, I was very interested. Parallel thought that's running is for my daughter. She can write that. Using computer all these days. Sometimes she uses it. Now she's high school. Here's the thing. She cannot express math concepts that are getting complex. Now she has started using that. She starts writing with it, and so like, oh, she should start writing it. I need to train her to that. Why should not to talk to?
So the whole of the practical literature, so we do study. So as we just started
No, it's not just the man. She's write something like saying, I did this thing in physics. This is how it looks. So some English to write. Then that's with the graphs. Yeah.
so the digital notebook, digital lab,
The mindset is not aligned to sort of focusing into the side. Very envious when I see Baltic navigation. They come on their own.
by the way, I will just ask you. Oh, sure, yeah. So
I just spent this week I don't know about statistics stuff about this week, like base theorem. I don't know, set the evidence number bound and everything. So I finally did out the which was how this paper was back, right? Like how wide yeah, okay, and I did please do. Okay. Yeah. Okay. Sure. And then I'm starting to get into looking at the code and seeing how I can, instead of using images, try to use audio. No, we do every that's exactly. Oh, we should transform it. It takes a square factor. It tries to it's point. Yeah. Vision transform. See, then look at that. Vision transform, we get the little patches. Okay, got you.
I sent you the name of two on the channels. Slack has the name of the channel.
Yeah. Yeah, exactly. Keep walking around. Sure. Okay.
All right, guys, our 10 minutes hopefully are over. We will now so we did gradient descent, and now we are going to change topics. We will go back to some real things. Before I do that, I would like to take an interlude. Just as last week we did, Harini showed her diamond data set. She has actually added a lot more to her data set. If you, Harini, are you here? No. So anyway, I have to change the LinkedIn link to her. But she has done quite a bit of improvement to her diamond data set, and it is now posted in the course portal. Please do visit it. Do I need to start the YouTube thingy? I suppose so.
It's already live.
It's already live. Kyle, would you like to walk through your Moringa thing, notebook, or should I do that for you?
I'll okay.
You
I
do
think
that.
I'll do it. Yeah.
You
Sure.
do. All right. So you share your screen and walk everybody through your Leaves project.
Oh, I think that would be a problem. Yeah. I have some issues sharing my screen.
Oh,
So
so
yeah.
I will. You talk, and I will share the screen for you. 1 second. Huh?
Okay.
All right. So just let me introduce you. So Kyle, of course, you're all familiar with. She is a data scientist here at Support Vectors. She is also a part of the teaching staff here, teaching assistant. And so this is a project. This is her submission for the Leaves project. It is still partial work. She has not looked at 2 species of plants. She has looked at 1, and she's continuing to work in that. But this is a work so far. Moringa is, of course, the drumstick plant we almost all of us have in our homes, right? And this is her project. This is Kyle, and if you want to look her up on LinkedIn, this is it. Most of you have been hearing her voice rather than seeing her. So this is her. She is probably the youngest member of our team here amongst all of you. So very, very motivated. So now this is the project she has done. So Kyle, please start.
Okay. So for this project, I collected around 20 compound leaves. So if you see the image below, that is one compound leaf. Like a branch, but it has a lot of sub branches as well. So the central, called the branch, the main branch, and then it divides into 2 on either sides, and towards the end, you have just one leaflet at the end. So the individual leaves, they're called leaflets, and these branches, they're called petioles. Petioles, I think that's how you pronounce it. So what we do observe is that it sort of is in a pattern. We see that it's in the it's all in odd numbers. We see that it ends with 1, and then you have these smaller, you know, I would say smaller compound leaves, or they're all sort of subsets of one another. So you have you have I would say a compound leaf of size 5, and then you have of 3, and then you have a 1, and then it's of 7 and 9. So it's all in odd numbers, and it seems like there is a pattern here. So I wanted to study that, and what I did was I took the size. So yeah, if you scroll down. So we see here that I took the I studied. I measured the length of one petiole. So I considered each of these. So we see that I have 5, say 5 compound leaves, or at least 5 clusters, and I measured the length of the petiole, and I counted the number of leaves that are there in each of these petioles. So so I did them for different sizes. So Asif, can you just scroll up to the previous image? Yeah. So yeah, here. So if I in this compound leaf, there seems to be there's like around 10 of these smaller leaves. Smaller compound leaves. So from one compound leaf, I took around 10 measurements. So around 200. I got around 200 measurements from around 20 compound leaves, and then I collected the data, and then I analyzed it. So if you could scroll down, Asif. Thank you.
Want me to go down more?
No. Yeah, this is it. So I did the basic descriptive statistics that we usually do. I saw. Okay. this is how I collected the data. We have petiole and a leaflet count, head and tail, and then a sample. And then I described data.describe, and we see. So one thing that I did, I collected the data for smaller PTO lengths more than larger ones. That was sort of by mistake, I would say. So we have more leaves of smaller size than of larger sizes. So as we can see in this plot, so I plotted my data set, and we see that towards the lower end, we have more data than that compared to those of larger PTO lengths. So, but also we can see some sort of not exactly linear, but some sort of exponential growth of number of leaflets with the PTO length. So, so at first I tried fitting a linear model to this and seeing how it performs that. Yeah. So, like I said, I collected more data for smaller lengths, and we can see that in the histogram. We see for smaller lengths around, like, so even I measured branch length of say 0.5 centimeter. If there were any, I calculated them too. So they were more in number compared to those of longer lengths. So because of that, we have more data for shorter lengths. So that's kind of evident from this histogram. And again, so this one is just, I tried doing standard scalar, but that kind of messed up things later on. So I removed it and I left it as it is. And then for linear regression model, so like we do with sklearn, I first split our data into training and test data, and then I fit the model to X-train and Y-train like we do. And so the coefficients that I got was -3 and 3. So that's what I get. And the mean squared error is around 22, and R2 is around 0.92. So it does seem like a pretty good fit, even though it isn't. So this is how it looks when I fit the linear model. The prediction line is it sort of fits the data, but still it's kind of obvious that it's kind of underfitting the data. So now I do a residual analysis, and we can clearly see there's a lot of pattern here, first of all, and then there's also heteroscedasticity. Yeah, it's pretty evident from the residual analysis. And yeah, and yes, the distribution of the residuals is skewed, and there seems to be bias error, and the model is oversimplistic because the model is oversimplistic. This one is the same histogram. So now since it appears to be exponential, I tried to do nonlinear regression, and I used the exponential function. Here, the function that I'm using is a into e to the power b plus c. So I'm trying to fit this function to our model, to our data. And so now when I see the coefficients that, so I use a curve fit, and I use the function that I created, and from that I stored my parameters and the covariance matrix. So from here, the covariance matrix shows that it's pretty much 0 in all cases. So probably is good in that the covariance is pretty much 0. And we see that for the coefficients only A is pretty significant, while B and C are pretty much 0. So it's almost like 16 e to the power x, 16 e to the power the PTO length. That seems to be the function that the model that seems to fit this this data. So now when we plot the function and overlay it on our data, it seems pretty neat. It fits the data. So for this, even though we do see some heteroscedasticity, which is not addressed in this analysis so far, the model still pretty much fits the data for now. So after which, I think Asif, I think you can explain what you think about this.
No. After that, no, we can. So one of the observations or feedback I'd given was that if you could continue this is a pretty good fit. If you look at this, clearly an exponential model has worked very well for this data, just looking at it. But you do see some degree of heteroscedasticity in the residual. So you ask, is there a different way to look at it? So one way that I thought we could look at it is, if you go back to the leaf, and that's sort of a physicist's way of thinking it, is if you look at this big leaf, right, and you think about it, you look at this leaf, for example, does it look like a triangle to you with a base, right?
Yes.
And so if in a triangle, barring some empty space here and there, you're looking at an area of the triangle. Very roughly, you can say that the area goes as the square of any of the sides or the heights, very roughly. It is clear that the width of this triangle is proportional to the height of the length of the leaf, the length of the petiole. And so one is represented by the other. So the area of the triangle, which is a good measure of the number of leaves, right, is therefore proportional to the square of the petiole length. So if you make that hypothesis, then I don't know if we did this experiment, Kyle, yesterday. I don't remember fully.
Yes,
what all things we did.
at the
So
bottom.
what you do is you create another data variable called area, and when you do that and you do plot area with the leaflet count, you notice that there is a little bit more. It is still spreading out. It's a little bit more. Did we do the fit here? We did the fit, y fit, and what was the mean squared error? Now we still get a mean squared error, which is along the same line. Did we do the mean squared error here? Area, leaflet count, determination, etc., etc. So that's another way to look at it. I don't know whether we did the residual plot or not.
No. But yeah, so when I was collecting the data, I realized that the thickness of the petiole also mattered, because if it is pretty thick, then there are more leaves compared to a thinner petiole. So I guess it is that could probably define. I mean, it be the reason for the heteroscedasticity that we're seeing, as and that happens only when the petiole length is pretty large. So for smaller petiole lengths, it's very standard. The width is pretty standard. But when the leaf is really large, the thickness also, I guess, matters.
That's right. But all of these are still very good models, because if you really look at the correlation between y, which is the leaflet count, and y hat, you're getting about 96% correlation, which is about as high as you can go. This is, in other words, all of these are very effective models. So a great project, Kyle. Very good job.
Thank you.
How many records in this data set?
She has about 200 something records for this one species. Yeah.
Just a quick, curious question here.
209. Yeah, go ahead.
I read somewhere the leaf patterns follow Fibonacci sequence.
They do. They very much do. And
so, how does that factor into our analysis here? Is there a model that represents that kind of scheme?
See, the way I would say that is this. See, first thing, so okay, I'll tell you this. There are multiple ways to look at it. First of all, yes, leaves counts. They tend to have a Fibonacci series pattern. One of the consequences of Fibonacci series is when the numbers are large, like for example, if you look at this compound leaf, and these are very approximate statements, guys. And so when you look at this very compound leaf, you notice a lot of leaves here. By now, these effects kick in. Now, the ratio of successive terms in Fibonacci series, it asymptotically, it goes to the so-called golden ratio, which is about 1.6. Now, I pay attention to this and see, when you look at this and you look at the length of this and you look at the width of this, does it agree with your intuition that this is approximately 1.5, right? The width is, the length is 1.5 times the width. Does it look like it?
Yeah, it does.
It is. So nature follows the golden ratio in surprising places, especially when you see compound leaves. See, when you look at nature, you find, and if you're interested in math and these things, as I told you, you see transcendental functions you see numbers everywhere. So one of the things I find interesting that in the animal kingdom, most things come in even numbers. You know, we have even number of hands, even and legs and so forth, right? But if you look in the animal kingdom, odd numbers are much more common. You count the number of leaves on any one of these and you'll see that they are odd numbers. Here, like count it. You see that they are all odd numbers, 3, 5, etc., etc. You can count it. In nature, in the plant kingdom, odd numbers rule. In the animal kingdoms, by and large, I mean, it's not that events are not there, events are there, but you see odd numbers much more frequently than even numbers. In the animal kingdom, on the other hand, you tend to see even numbers much more, right? And when you see compound leaves like that, right, all these things come. So anyway, that is an answer to your question of the Fibonacci series and all of this, golden ratio and so forth. Does that answer your question?
Yeah, somewhat like that. My thing was like, is there any mathematical models that can be used for Fibonacci? It's like, for sometimes these kinds of oddities, like the Fibonacci, the factorials and things like that, they sometimes trip you in some pattern which we don't recognize.
Yes. Yeah, see, here is the way I think about nature. The nature and the world, frankly, is written in the language of mathematics. Right?
Yeah.
So if you, one metaphorical way, a poetic way to say it is that if you want to read the mind of God, learn math because his thoughts are in, or her thoughts are in mathematics. It's the language of mathematics, right? And in India, we have all these stories of Ramanujan being inspired by a goddess. You remember those stories, isn't it?
Yeah.
It is the language in which the whole deep mystery of the universe is written. And I would always recommend people that learn math first. Everything else becomes easy after that. Right? You notice that when I'm teaching you machine learning, it's very different from the way most people teach you.
Yeah.
Most people teach you code onwards. Oh, here is a code. Here is this library. Do this. This will happen. Right? Whereas I go to the mathematical foundations because I feel that if you understand the geometry, if you understand the math deeply, then language, Python, R's, all of this color, this, that, they will keep coming and going, but your understanding will remain.
It's true. Thank you, Asif.
Sure. All right, guys. So we'll do another data set. This is an interesting data set. So you have to assume that you don't have real world experience with cars yet, right? So imagine that you're an alien and you have come to this planet and you observe that people tend to move around in these automobiles, right? And these automobiles are characterized by their horsepower, their weight, and they have these engines. Engines have displacement. What is the displacement of an engine?
The CC rating that you provide?
Now,
cubic centimeters.
see, what happens is that think of an engine cylinder. The cylinder of an engine is like this. Yeah. So what happens is that this thing, this part, it increases and decreases because inside there is a piston. And what the piston does is it pushes its way in so that the available air gap, the space available or the volume available decreases. Think of it as an injection, the way you do it in an injection. So you compress, the piston goes into the cylinder, the available space is very little. In that available space, you spray a mixture, atomized mixture of gasoline and air. And once that is saturated, that mixture saturates that volume, the spark plug, you have a spark. And what the spark does is it ignites that atomized mixture of air and gasoline, and it literally explodes. There's a fire, it burns. There's an exothermic reaction. Exothermic reaction creates temperature, temperature creates pressure, pressure pushes the piston back. Right?
Yeah.
So the piston goes all the way back, but when it goes back, it doesn't just go back. Behind it, at least in the early design, there was a crankshaft, right? So what it would do is it had a camshaft design. It was a wheel there. Basically, there's a way that to convert this backward motion into a rotation. And so it causes a rotation of something, right? And that rotation forces the cylinder back, because here what has happened is once the exothermic reaction is over and the fuel is consumed, now this can push back because there's nothing creating the pressure and so forth. So this can go back because a port opens, which lets the exhaust gases to leave once the combustion is over. So now this piston can go back because it will force all the air out of the chamber, ignition chamber. And this piston goes back, and then the cycle repeats. As it goes back, more atomized fuel mixture comes into the chamber of the cylinder and ignites, and this thing again goes back. So you have this piston going back and forth, the camshaft, and it's causing a rotation, right? And that rotational motion is further propagated. And that is basically your internal combustion engine, right? Or very similar to similarly a diesel engine, etc., except that you don't need sparking there. So that's how these fossil fuel engines work, basically. So now what are the criterion? You're trying to determine how much miles per gallon of fuel can you get from an automobile. That's the target variable. Now, what are the features that matter? Common sense says that the sheer weight of the car or the automobile matters, right? Or for example, if you bring a Humvee, which is, I believe, 5 or 6 tons, then the amount of mileage you expect would be different from the mileage that you would expect from a compact Prius, right? So that way. And then that another factor that matters is horsepower. Horsepower is like how much horsepower does the engine manifest in terms of its pulling weight, how much can it pull, right? And horsepower literally started with horses, what the standardized might of a horse. So today we run cars with massive horsepower that is unimaginable. I mean, we run cars of 500, 600 horsepower. We never really think about it. It's fun to drive those cars. But if you really think about it, 600 horsepower is 600 horses are pulling just you, right? The army of horses pulling just one person. So obviously, these are very powerful engines here in the US. Then the other thing that matters is cylinders. So how many of these chambers or cylinders act in collaboration or collusion to cause those rotation, right? The primary rotations. So the more the engine, the better. In US, you talk of the so-called V engines are the most popular for the last 100 years. So the V-shaped engines have a body in which the cylinders are along the V, on the tip of the V in a line. There's a line of cylinders. So you can see, open your car and see that. So we have V4, which is the default. V6 is supposed to be for more powerful engines. And then if you really need a muscle car, then you go V8. And if you really have no consideration for money, you can go to V12 or something like that. So there are such engines. So number of cylinders matters. The V2, V4, V6, V8 represents the number of cylinders. So the cylinders are there, the weight of the car matters, the horsepower matters, and then the word acceleration matters. Acceleration, when we talk of a car's acceleration, we talk of it like this. In US, you talk of it in an interesting way. You say how many seconds does it take to reach 60 miles an hour, right? So if it takes 10 seconds or 15 seconds, it must be a very, very weak car, right? If it can do 60 miles an hour in 3-4 seconds, it's a mighty car, right? And so the acceleration is a very peculiar in this data set. You have to remember that it is not in the literal sense. A physicist would say the stronger the acceleration, the more powerful the car. But here, the way we speak of in acceleration in the car industry is how much time does it take to reach 60 miles an hour, right? So acceleration, therefore, big is weak car. Small acceleration is powerful car. That is one thing about this data set you should remember. So with that, all of that there, this data set was collected a few years ago by looking at automobiles of 3 countries. That countries is given by the origin. There's a feature here called the origin. You will see. Do you notice that origin of the data set? I load the data set. You see origin. So one is US.
Can you zoom in a little bit?
Sure.
Yeah, and also the initial graphic that describes the issue.
Oh, yes,
Yeah,
yes.
I'm not
So
seeing
this is,
that.
by the way,
That's
literally
broken
question
in mine.
8 and question 9 of your ISLR textbook. Right?
Okay, it's in the textbook.
Yeah, it is quite literally in the textbook. Let me,
Okay.
ISLR, okay, yeah. If you did, okay.
Yeah, because that PNG is missing.
Ah, okay, I should upload that. I apologize. So it is literally question 8 and question 9 of chapter 3 of your textbook. Right? So this is how the data looks. If you sample the data, you notice that miles per gallon, you can imagine that this is, would you say these are impressive miles per gallon by modern standards? Probably not. Most cars don't give much higher mileage. People are shooting for a 40, 50, 60 these days, right? As miles per gallon. Especially the 4-cylinder engines easily give you these days 50, 60 miles a gallon, especially if they're hybrid. And the 8-cylinder engines, of course, it is 15 miles a gallon. Do you think that is still reasonable, or that's low or high?
I think it's a good, yeah, it's.
That's what you did right now.
Yeah, actually,
Terrible.
that's
Prius
what
gets 40.
that is what my car gives me. My car still gives me 15 miles a gallon.
Oh.
It's a V8, right? So displacement, now you see, displacement is literally a measure of the size of the cylinder, because it is how far back the the piston goes back and forth. What is the displacement of the piston? And that, of course, would be a measure of the size of this can or the cylinder, right? That's what it is. Number of cylinders, and think of it as sort of the size of the cylinder. Horsepower, how many horsepowers is it manifesting? The sheer weight of the automobile, right? How much automobile there is. Now remember, acceleration is how many seconds it takes to reach 60 miles an hour. Obviously, in those days, this used to be the amount of seconds it used to take. Today, how long it takes? Much, much less. The engines are far more efficient and powerful, right? And this is a display. Yeah, see the same sample. There's some statistics here. Miles per gallon, the mean is 23 and standard deviation is about 8. And maximum mileage you used to get is 46.6. And the minimum you get. Now, one more thing here, displacement, everything. Year. The minimum year is 1970 and the maximum year is 1982. Right? So it is a study done over 12 years, over 400, about 397 data sets, right? Now, origin minimum and maximum values are 3. You can see that there are only 3 possible values, 1 to 3. Now, if you read the documentation behind this data set, go back to the original paper, it mentions that 1 stands for USA, 2 stands for Europe, and 3 stands for Japan. Yeah. Japanese make. European make automobiles, I mean, American made automobiles, European made automobiles, and Japanese made automobiles. Right? So let us do the basic exploratory data analysis. The first thing you realize it takes a while to realize that something is wrong with horsepower. Do you notice that all of these mean, medians, everything is missing? Why would it be missing? You expect name. You see the name Ford Pinto. You can't have it is a categorical variable. You can't have mean, etc. for categorical. It makes sense. But what's wrong with horsepower? If you look at horsepower, you suspect something is bad. And so you can check, maybe some values are not numeric. And when you do that, you find that, yes, truly, apologies.
Bless you.
It's just my allergies. So X for X in unique values if numeric. So what happens is there are about 6 data points that have question marks. You can check, right? 6 or 7, I don't know which exact number. So they are missing values there. What we will do for now is just delete the missing values, right? So we do some data manipulation in the beginning. Right? This is real life data now. You have to deal with the fact that some things will be missing, some things will not be okay. So what I've done is I've converted horsepower wherever it's missing. I've deleted the row altogether. And then after that, I've converted those values to numbers, because horsepower should be a number, isn't it? Right? It should be a number. I've converted it to numbers, and origin, which is a number, I've done the reverse. You know that these origins these are not numeric. 2 is not greater than 1. 2 is just a representation for Europe. 1 is representation for US made vehicles. 3 is for Japanese made vehicles. So I've converted horsepower to numbers and origins to string. This is basic data manipulation to clean it out. Also, I realized that if you're trying to predict the name of the mileage of a car, do you think name is a good predictor? No, because if mileages could be changed by name, most manufacturers would go about finding the optimal name to improve mileage. Right? It doesn't make sense. So that is that. So I just drop name, forget name. After that, I noticed that the data looks clean. Missing number analysis shows data is clean. Info, everything is as it should be. Miles per gallon is a float, is a numeric. Number of cylinders is integer as it should be. Weight for some reason is mentioned as an integer. I could have bothered to convert it to float. I didn't bother. Right? Year the car was made is an integer. This is it. So now let's go. One of the things I didn't do is this profile, because it takes a while to run. You can uncomment and run it on your local environment. So now I take this and data visualization. You visualize the data, right? So let's look at it case by case. We are looking at miles per gallon. Is this data symmetric? No, it is skewed, isn't it? And it is right skewed. So we need to worry about that. Number of cylinders, well, you don't get cars with odd number of cylinders. There seems to be some data point which is unusual, but be as it may. Most cars are they, what are they? Most cars are V8s or what are they? 4 cylinders. 6 is, in those days, was not so common. V8 was very common.
4.
Of course, the situation has reversed. Today, we get a lot of 4-cylinder and 6-cylinder cars. V8s are rare, fairly rare, actually. It's hard to get a V8. A bit of personal thing. I actually grew up with V8s right from the beginning. I used to love sports cars. And of course, now I'm in my 50s, so it's a bit of an anomaly. But because my hand and my reflexes are tuned to a V8, as I grew older, I don't drive very fast. But because my hand and my complete sense of braking and everything is attached to a V8 engine, I still drive a V8, which looks sort of anomalous, because here is a person going in a V8 and driving in a sedate way rather than accelerating like a young man, right? But so it is what it is. Displacement, how much displacement? So most cars have small displacement, but yes, data does have a skew here. Then we look at horsepower. Again, most cars don't have that much horsepower in those days. Wow. Most cars didn't even have, most of them were 100 horsepower or low. That's world has changed. Weight, again, a right skew distribution. Acceleration seems roughly speaking, evenly distributed, isn't it? Acceleration is this. And the year of the car, how much cars were made in each year. Then I count the number of cars by origin, by country of origin. It turns out that US is the biggest maker of cars. Number 3 was Japan. Japan makes also a lot of cars, and Europe makes the least number of cars, just a little bit behind Japan. But US is, of course, the land of cars, right? It's always been the land of a lot of cars. Let us plot this data. Now, this plot is interesting, and there is a lot going on here in this plot. I want to show you what it is. So I will just, because it's a blown up the screen, this is a big plot. So let me just for one moment shrink the size and show all in one. Even then it's not okay. Of course, you have to squint to see this, but you notice that this is a pretty busy plot. About 6, 7, 1, 2, 3, 4, 5, 6, 7, 8, 8 variables plotted. The way I've done it is, and the way this plot works is called pair plots. The diagonal is the frequency plots, histograms, right? Then these ones are scattered top half. The top above the diagonal are the scatter plots between two features. Below the diagonals are this kernel density plots, so that we have everything now. So now let me just blow it up and show a few examples to see what it means. So look at this. This is the histogram. The way to look at it is histogram, miles per gallon versus what? Miles per gallon. This is the Y, this is the x-axis. So intersection here is miles per gallon. This is the histogram we just saw a little while ago for MPG. This is exactly the same as this MPG, right? Miles per gallon thing, MPG. This is it. Now let's look at this row. This row is miles per gallon is along the y-axis, and the x-axis is cylinders. Of course, you have to scroll down to see the word cylinders here. So this is the cylinder, right? I'll make it even bigger. Yeah, cylinders. So what does it say? As the number of cylinders increases, does miles per gallon improve or decrease?
Decreases.
Decreases, right? You notice that with V8 engines or the 8-cylinder engines, the miles per gallon is pretty low. Whereas for 4-cylinder engine, the miles per gallon in general, the middle is somewhere here, pretty high. The next feature is displacement. Here, the x-axis is displacement. How would I know it? I can scroll down and see, yes, it is displacement. Other thing, the way I use it is I just look at the order here. Third is displacement. So here, miles per gallon goes up or decreases with displacement. What would you say, guys?
Decreasing.
Decreases. But is the decrease linear, or what does it look like? It's a
Like
non-linear one, isn't it?
Like more like
Sloping down.
Yeah.
it's looking down, yeah.
Yeah. Likewise, the relationship of miles per gallon with horsepower is like this, right?
Mhm.
Which is sort of disappointing. Wouldn't it be a teenager's dream that mileage improved with horsepower? It's one of the disappointments. The moment you run big cars, sports cars, the whole thing just guzzles up the gasoline, and it makes you feel guilty as well as disappointed. But it does. That's what it is actually. So the next one, actually, I have a little thing. My daughters, I gave them pretty much the similar cars to mine because they liked it. So they were very excited in the beginning. Then gradually they went to college, and I had given them fixed pocket money to fill the gas tank. You can imagine the disappointment.
They'll curse you.
What's that?
They'll curse you for
Yeah.
giving them.
Because they say, this thing just guzzles up the gas.
They can't eat with the pocket money. The car will eat everything up.
Yes, exactly. So now they came and negotiated that I'll pay for the gas, and they will not pay from their pocket money. So this is a lesson that you see in this graph. Next is weight. So what is the relationship of miles per gallon to weight? Shouldn't you have seen a reciprocal relationship? The more the weight, the less the miles per gallon. Why is there no clear relationship?
There could be difference in the materials used, plastic versus
No. It
steel and
is.
stuff.
Sorry. No, this is weight. It is weight. It is a reciprocal relationship.
It's the inertia.
Yeah. The fourth is acceleration. Why does acceleration not have anything to do clearly with miles per gallon? Do you notice that the relationship is not so clear? You would imagine that the bigger the acceleration is, the longer it took to reach 60 miles an hour, the more the mileage, because weak cars, they take a long time to accelerate to 60 miles an hour, and they give you perfectly good mileage, but you don't see such a good mileage. Why is that? I will leave that as an exercise. The answer is quite simple, but I'll leave it as a food for thought. Should you want me to answer that?
Maybe the newer cars got better engines, that they are more efficient. It's a 182, right? So 12 years of difference. So that's a mixed number of efficiencies there.
Repeat the question, I think.
Why is acceleration and miles per gallon not having a very pronounced and simple relationship? The more the acceleration, the longer it takes to reach 60 miles an hour, the weaker the car, you would imagine that the more the miles per gallon.
No, this also function from the size of the car.
Exactly. So the size, what happens is sometimes acceleration, longer acceleration is not just because of a weak engine. Longer acceleration is also because you're sitting on a big, massive engine. For example, most buses are heavy, right? And they have pretty weak acceleration. They take a long time to reach 60 miles an hour, right? But so that is the explanation. The year also matters. I think one of you said year. Year is also a factor that interplays. The next one after acceleration is literally the year. So this is year versus miles per gallon. So I'll just blow it up. What do you think, guys? Are the cars improving with respect to their mileage, fuel efficiency, or getting worse with years?
It'll be better as the year goes by.
Come again?
It'll be better as the year goes by because advancements come up.
Yes, exactly. If you draw a line through this, you can literally feel that, yes, slowly, steadily, slow and steady improvement in mileage with passing years, right? Cars are getting fuel efficient in the 90s, of course, by 82. And then, of course, in the 90s, people discovered SUVs and the whole situation got worse. Yeah? So it's never linear. Anyway, now you look at the country of origin. The last one is the origin, I believe.
See, one quick question on the previous plot. Right?
Yeah.
In some of them, they have clusters broadly identified, but in some, they're not. So it looks like Matplotlib is using some kind of a determination.
No. Here is a discrete integer variable, no?
Okay.
So it takes integer gems, 1, 2, 3. Likewise, the country of origin, 1, 2, 3. So you see that mileage of American cars are terrible. Mileage of the Japanese cars are best. Mileage of the European cars are slightly worse.
Look at row 2, first column. Like it has those little black lines. First column. That's the difference.
You mean this one?
Row 2, first column.
Oh, this is something different. I'll explain that. So I'm still interpreting the first row.
Okay, sorry.
So in the first row, origin, the number 1 stands for American cars. They always traditionally had bad miles per gallon. Japanese had better, and Europeans were comparable to Japanese. This is, by the way, this fact, unfortunately, is still true. You probably know that the same car manufacturer will make exactly the same car, but in Europe will give much better mileage than in US. Right? So some of the fuel efficiency components, because they are expensive, they will not get installed in US. Right? Because the laws here are not as strict as in Europe. So the same car will give much better efficiency there. Can't do much about it. It's a fact of life. We have to get the laws changed. California is doing its part, but let's see. Now let's look at this guy. Look at this second row now. This plot is interesting. It's below the diagonal. Do you see that? These are called kernel density plots. It plots, well, we talked about kernel density plots. They plot contours of equal value, right? And what they tell you is, well, okay, they say a lot of things which I don't want to talk about till we get there. But basically, they show you that how is the data distributed. So clearly, data is distributed around 6-cylinder, 4-cylinder, and 8-cylinder. Do you see these bands of data, right? And it is a cylinder versus miles per gallon. And you can clearly see that 4 cylinders gives you, the center of it is more to the right than the center of the 6-cylinder than the center of the 8-cylinder. What does that mean? The average miles per gallon from a 4-cylinder engine is far more than from a 6-cylinder is far more than from an 8-cylinder engine. You see that, right? So that's what you get from this density plot. So this is the way you interpret it, guys. I'll let you interpret. The most important line was miles per gallon and its relationship to each other. But then I'll show you something quite interesting. Look at this plot and look at, for example, displacement. What is this guy? Let's look at this guy. This is displacement versus what? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Displacement versus weight is this. This plot. Can you guys see where my mouse is? What would you say?
Yes.
Looking at this graph, what is the correlation between the two? Displacement versus weight.
Positive.
Very, very strong correlation, right? You can see a strong positive correlation. You also see a strong positive correlation here. You see a strong positive correlation here, right? So while correlation of a predictor to response is a good thing, correlation between the predictors for linear models is not a good thing. It leads to a pathology which is called collinearity. What it means, I'll give you the intuition. We'll talk more about it. The intuition is, if two variables, they are giving you the same information, right? So how should I say it? Let me make it a joke. See, guys, we come from the software industry where we are supposed to work often in pairs or groups, right? Have you noticed that once some work is done, the first person who goes and talks about it pretty much steals the thunder of everyone else, right? If he doesn't give the credit or she doesn't give the credit to the entire team, everybody will think this guy did great work. The next guy who comes and explains it has almost nothing new to add. You know the phenomenon, right? It's literally somebody has stolen your thunder. You're going to say something very impressive, but somebody said it already, right? That is it. So when two things are highly correlated, right? For example, you look at two variables. One is the height of a hill above sea level, and the other is the height of the hill from this valley below, right? From Fremont. You would agree that the two variables will be very correlated for the regional hills behind a house, behind support vectors, right? Next to this mission peak that is there and all these hills around you, you would imagine that these two variables will be highly correlated. And if you think about it, you don't need both. You just need one, because one is as good as the other. Height above sea level and height above Fremont. The only difference will be the height of Fremont above sea level. Do you get that, guys? Does that make sense, guys?
Yeah, got it.
Right?
Yes.
So if you have two features, one is height above sea level, one height above Fremont, you would say that they are very, very correlated up to some noise factor. And common sense says we don't need both. So what happens is that it shows you the redundancy of information in your predictors. And for linear models, that sort of redundancy is not good. That high correlation between them is not good. And there is a word for it. It is called collinearity, or more formally, multi-collinearity. What it does, it screws up the machine learning model. it causes, and there are many things it causes. Let me not steal the thunder of Tuesday's session, but it basically causes problems. So you have to watch out. When you see that, you should eliminate, you should pick amongst the highly correlated factors, one factor, and drop the other ones. So that is that. So now looking at this, we make some more plots to see the distribution of the data. These are called Violin plots. We see the data distribution of each of the variables, and I've separated it out by origin. So you can see miles per gallon. Well, most American cars used to give about 10, 15 miles per gallon. The Europeans used to give 25 miles a gallon. The Japanese used to give, oh God, they already were giving 30s gallon. So these are Violin plots. I mentioned it to you. They're common, they're pretty, they're useful. And an alternative to them are the box plots. These are called the box. Oh, I shouldn't say Violin plot. I should change it to box and whisker plot. I apologize. Box and whisker. Box plot of the features. This is the box plot. So in the box plot, this is the middle value, median value. This is the way the data is distributed. The sort of average data is distributed. The whiskers represent the, I think, the quantile limits, Q, right? And then these are the outliers. So these are the standard box and whiskers that you used from college. Then you look at the correlation between the data. I'll slightly decrease the font to show the correlations. So when you look at this correlation table, guys, do you notice that miles per gallon is correlated to number of cylinders negatively? The more the number of cylinders, the less will the miles per gallon be. Does this agree with common sense?
Yes.
Right, it does. Displacement also, the bigger the cylinders, the worse the miles per gallon. More powerful a machine you have, this heavier the machine you have, less the miles per gallon. And the more the acceleration, the more the miles per gallon. But by acceleration, the meaning is inverse. How long it takes to reach 60 miles an hour, right? And also it has a positive correlation to years. So the more recent the year, the better the mileage. Does this all agree with common sense, guys? First row?
Yes.
But now comes trouble in paradise. Let's look at any one thing. Let's look at the weight. Weight, okay, MPG is fine. But you notice that it is highly correlated with cylinders. What does it mean? Heavy cars tend to have more cylinders, which is common sense. Big heavy cars, they tend to be V6, V8. Displacement, even more, 93% correlation. Horsepower, again, a lot of correlation. So what does that mean, guys? That if I take weight, maybe I can forget about a couple of these variables. These are highly correlated variables. At least these two I can forget about. Maybe keep horsepower, may not keep horsepower. But this is close to anything like 90%. You don't get much value by keeping those variables, right? So let's do that. First, what we will do, and then this is, by the way, same correlation plot visualized. Very negatives are black and very positives are light and so forth. So the same information visually displayed. So now let's do one thing. Your book talks about doing analysis. What's the time now? Oh, it's 5 o'clock already. So actually we are still an hour or so away from the thing. Are you guys open to a long session, or should we finish at 5:30 and take it up next week?
I need to head out in a few minutes, so maybe I can drop and see the recording later.
Let me finish at least the auto data set, and we'll keep California for next week. So the first part of the question 8 in your textbook says, do a univariate linear regression. Treat horsepower as the input, miles per gallon as the output, and see what happens. So we do that. This is the plot of horsepower to miles per gallon. What do you see, guys? Does it look like a linear relationship to you? No.
Looks like a slide.
Yeah, it looks like a children's slide. Yeah, that's a very good observation. Looks like a children's slide. So what can we do? My intuition, and whenever I see this, of course, this is the habit of years. If you ask any physicist, the very first thing they will tell you is, hey, this looks like 1 over x to the n graph. This is, I actually mentioned this to engineers, and I was surprised that most engineers don't think like this. They don't think immediately a reciprocal power law, a graph. They just say, okay, there's a, it doesn't look linear, but it is. And the only question that remains is what is n? So if this relationship is like that, what is the simplest way you can make it into a linear relationship? How can you linearize it? Old trick, just take the log of both sides. If you take a log of both sides, do you see that this relationship now becomes linear? Y is not linear in x, but log y is linear in log x, isn't it? So if you think of new variables, y prime, which is the log of y, and x prime, which is the log of x, you see that y prime is proportional to x. Do you see this, guys? It is obvious. Anyway, so what we do is, we can verify my intuition. You can take the log of both the sides, and what does it do? Would you call this essentially a linear graph now?
Yes. Yes.
This, by the way, it's a very common thing. I have seen so many people struggle with data analysis. This relationship, inverse relationship, will be staring them in the face, and they won't spot it, right? And I hope you are not one of those. You will learn to recognize the inverse relationships and immediately know that when you see inverse relationships, you should take the log, right? Whenever you see what Kate nicely said is a slide, the shape of a slide, immediately take the log of both sides, because that will make into a linear relationship. And so we can do that. If you don't do that, if you do the regression in the original variables, you will get you'll get some intercept, something, you get the prediction on the test data. What is your R square? 56.5%, right? 56.6%, let's say, is your R squared. Your residual analysis, what does it show? Does it show homoscedasticity?
Yeah, there's a lot of pattern.
There is a lot of pattern, and there's a very clear increase in the variance, right? So there is a distinct presence of heteroscedasticity here. Then here is one more plot that is useful. Predict the if y and y hat are completely matched, then they would be along a 45-degree axis. But actually, when you plot the y and y hat and you look at the best fit line, you notice that it is tilted, right? It hasn't gotten the relationship well. In the lower part, y hat is an overestimation. And after, in the right-hand part, like after a little bit, it is a underestimation. So somewhere systematically, you see the bias here. It is overestimating here, it's underestimating here, right? So when you visualize the model's prediction, you can see it distinctly. Do you see this? Very distinct thing, shape. Would you call this line a good fit to the model?
There's still slide shape in the data.
Yeah, you can, but all it shows you is maybe you could go with it, but there is a scope for improvement, right? There is a scope for improvement. So now let's try the log transform, the way I mentioned. Take the log of these two. When you take the log, repeat the analysis, what is it? Your R square went to 72%, right? 71.8. So from 55, 56, you go to 72. Would you consider that a huge improvement?
Definitely.
Yeah, in business, in real life, that would be considered a huge, huge improvement in terms of real value, right? So it's a much better thing. How about the residual plots? Does it look better with respect to the patterns?
Yep.
Very much.
Yeah, patterns have not completely gone. There's still a distinct slight noticeable there, but much, much improved. And what about the prediction line and versus the best fit line? You notice that these are much closer now, right? It is not so far apart as here, where they have like huge gaps here. The gaps have narrowed. right? This
Yeah.
is, so this is, and then when you visualize the model prediction, because now you have taken the log transform, would you say that the model and the data are in good agreement? The prediction and the data are in good agreement?
Yeah,
They are.
definitely.
And
Yes.
already you have 72% this R squared. So your things have improved. So guys, this is the power of bringing intuition, physical intuition into a problem. If there is one thing I can say, learn mathematics and learn to apply mathematics. I can't say that enough. I mean, if I have to quantify what I have learned in life over 50 years, or more actually, much more than 50 years, but let's say, without giving my exact age, let's say 5 decades, what have I learned through education? One deep lesson I learned is know your math really well. Not from the point of view of exams and passing and getting good grades and things like that. Really have a deep feeling for math. Just as you can speak your native tongue, speak in the language of math. And wherever you see things, see that the thing, can you interpret it, reality in math, and see what is going on. If you do that, you will actually do very well. So one point I was going, and this again is drifting away from objective and going into my subjective experience in this field. See, I did this, I did the log transform, but suppose you said, no, wait, what about the fact that we already have a power transform, Box-Cox and a Yeoman-Johnson transform? What if we use that? Wouldn't it give you the same results? No, a blind use of a power transform. You knew that a power transform is called for. Why did you know that? Because both horsepower and MPG had right skew. See, look at that. Miles per gallon has a right skew and horsepower has a right skew. Do you see this, guys? Maybe more evident here. Miles per gallon has a right skew, and where's horsepower? Horsepower has a right skew. Therefore, you could have said, yeah, let's apply power transform. Let's find the right relationship and all of that. What happens if you blindly use the tool, which is what people would do? So the general reaction of people is, yeah, data is nonlinear, so I need to apply power transform. Yes, you can apply it. When you apply the power transform, I make a pipeline of the power transform and linear regression. What happens now? Do you notice that your R square has gone up by gone up from 55 to 64%? That is a huge improvement, isn't it?
Mm-hmm.
But is it the best model so far?
No.
No.
We got the log better.
Because just by using our judgment and hand thinking that we need a log transform, we got 72%. 64 is a far cry from 72, which again, I wanted to bring home the point that, guys, think about data, make friends with data, know the data so that you can do it. The next question is, what if I tried polynomial regression? Won't polynomial regression give me the bends I need? Once again, if you do it, what happens? It is close to, it goes to 66%. Nothing close to 72%, isn't it? Do you see how hard it is to beat well thought out models? If you can see things in the model and you can recognize it and do your own transformations by hand, nothing will beat that. No automated blind application of tools will help that, right? So that ends the one-dimensional or one variable regression. Now the problem number 9 is to do a full analysis using all the predictors. So let us use all the predictors. Now there is a problem. One of the predictors is origin, which is like US, Europe, and Japan. 1, 2, 3. How do you deal with that? So what you have to do is dummy encode it. You have to convert it into numbers, categories into numbers. One way of doing it is it's called one hot encoding. You say, you create 3 features: origin 1, origin 2, origin 3. Actually, I should have named them origin US, origin Europe, origin Japan, but okay, I was lazy. And then if it is a US made car, you say origin 1 is 1. It's true. And for Japan and for Europe, you mark 0. If it is a European car, you mark origin 1 is 0, origin 2 is 1, and origin 3 is 0. You see that, right? Origin Europe is 1. So that way of doing it is called one hot encoding. So partners give you a very simple way to do one hot encoding. You can just say get dummies. And you notice that it got burst out into 3 variables now, 3 features. Now, I want to tell you something about a most useful regression model overlooked. Before you build complicated regression models, right? You see one dimension, we use this null hypothesis, etc. In the equivalent, the closest thing to null hypothesis, and in fact, practically the null hypothesis in scikit-learn is the dummy regression. What the dummy regression will do is, if you ask it to predict something, it will tell you, should I predict the mean, median, something, right? Remember, the null hypothesis would just return you the mean, right? The mean of the target variable. Do we remember that, guys? The null hypothesis returns the mean of the target variable in the data set, in the training data. Always as the prediction. Whatever the input, it will always predict that mean. Because it's the sensible thing. Because what does the null hypothesis say? There is no relationship between target and predictors. So the best prediction that you can have with the lowest sum squared error is just to return the mean. And so dummy regression is in that same category. You can return mean, median, mode, whatever it is. But here, just to emphasize the fact that there are multiple choices, I took median, not for no big reason. I noticed there was a small skew in the data, so I just took median. Null hypothesis has a, what is the coefficient of it, R square that you should expect from a null hypothesis? By definition, 0. TSS minus TSS is 0, right? So this is it. And you get a lot of mean squared error. So you should always compare, because what you should look for is the decrease in mean squared error. Let's keep our eye on that. We take a model 1, no transformations, all the predictors in there. Right off the bat, we get just blind utilization, we get 80%. What does it tell us? When we take all the predictors and we apply, what does it tell us? It tells us that horsepower is not the only thing that matters. In the only the horsepower-based model, there was a lot of irreducible error, isn't it? That error captured the information there in the other predictors, which we had not considered in the previous models. Now that we are doing multivariate regression, we are taking all of those right away. It has improved to 80%. But when we look at the residuals, of course, what do we notice? We notice, yeah, there's a pattern, there's heteroscedasticity. We move forward. Again, we notice that there is a gap, not so much gap between prediction and this, but there is still a pattern. So let's take to model 2. This time we remember to standardize the data. We apply the power transform, and here we go. When we do this, do you notice that your mean squared error is continuously decreasing? Is there? Your R square has gone to 81.6. Better. Then, what about the residuals? Residual still has pattern, isn't it? Some pattern is there, despite the power transform. But the errors seem to have a more or less an even distribution now, right? Let's move to another model. Model 3. Model 3, what did I tell you? Log transform, hand-built model, right? Let us go and take the log of weight, MPG, and horsepower, these three. Also, we realize that it has a strong correlation with other things, displacement and cylinder. Let us go and drop those variables, right? Because that would cause multi-collinearity effects. When we do that, what happens? Look at this R squared. Close to 87%, isn't it? Do you see this, guys? Right.
Nice.
Once again, the same lesson holds. When you carefully handcraft your features by looking at the data and bringing your own judgment on it, you always get the best model possible. Now, given these things, you can try to improve upon it. You may do it, but not by much. 87% is about as far as you can go, right? Residuals of the learning. And do you notice that between the best fit line and the 45-degree y-axis, there's almost no difference. You see this, guys, here?
Wow.
Yeah, it's pretty good. So clearly, we have a vast improvement over the prior models. So now let me teach you one more thing. It's called the Cook's distance. It talks about points of high leverage. Let me explain what these points of high leverage are before we end today. See what happens with linear models. Linear models are the simplest models. Obviously, we'll deal with other kinds of models. Linear models suffer from many problems, three of which we had talked about. we'll talk about. One is the multicollinearity. We talk about it next time. One is outliers. So when you do sum squared errors, what happens if that one point is way up there, away from the other points? It will exert undue influence because it's an outlier. Do you see that? Right? So because the sum squared error of that will be huge, and so it will have unusual effect. The loss function optimization will keep on trying to optimize for that outlier, and it will pretty much pull the line towards itself. So outliers have exaggerated influence, right? So you may say, well, no, you can change the loss function to mean absolute error, do something like that. But anyway, outliers are a problem. But the point with outliers is they're visible. You can see that they are outliers, right? And you can do something about it. But linear regression models suffer from yet another problem, which is very hard to see. It's insidious. It's points of high leverage. It's like these quiet people in the sort of like the team who are invisible, but they're the puppet masters, pulling all the strings, sort of like that, metaphorically speaking. In this data itself, there'll be certain points which have undue influence on the training of your model. When you look at this, there are a few points, but not that many. Usually, anything above this line, dotted line, red line, this is called the fence. Points above the fence whose influence is more than the fence, they do have. So how many there are? 1, 2, 3, 4, 5. Let's leave the small ones actually. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About 10 points out of 400. It's okay. You can either read them out or you can just leave them there. It doesn't matter. But you don't have as many as to get alarmed with. Still, you do get the impression that maybe instead of using linear regression, we can try more sophisticated models which are immune to points of high leverage, right? Then comes the last question. Okay, before I take the last question, guys, I need a 2 minutes break. Give me 2 minutes. So suppose, see, feature importance is a very important topic. It addresses the fact that suppose I brought predictors. In real life, in business world, it's a day-to-day. How important really is this predictor in the model? Right? How much influence does it have? So for example, let's take diabetes. The likelihood that you have diabetes, how much more, whether you take sugary drinks, is it going to make it worse? Like what makes diabetes worse? I assume that you have diabetes. What do you need to watch out for? Do you need to watch out for the amount of sugar that you take in food? That matters more, or the color of shirt that you wear while eating the food? Which is more important? So would you answer that? How would you answer that?
Your
Good
food
amount of sugar you're
consumption.
taking.
Exactly. The amount of sugar that you take in your food has overwhelming importance relative to a frivolous factor, such as what colored shirt you wear while eating that food. Yeah. But in the absence that you are saying, because you have bring experience to it, when a machine does it and you don't know which features are important, the most important question that you have to ask the model, one of the most important is, which factors were the most important in making the prediction, right? What mattered? Do we get that? What mattered is one of the most important questions you can ask the model. Yeah? The model has learned something. You want to ask the oracle, what did you learn? Right? So that answer is the feature importance question. Now, the thing is, if you have standardized the data, then in linear regression, actually feature importance is very straightforward. You can literally see the power of the coefficient. Why? Because if beta 1 is twice beta 2, means if I increase factor, the x1 factor by 1 unit, the increase in y will be twice that of the increase if I increase y x2, isn't it? So suppose x1 and x2 are two factors. X1's coefficient is 2, x2's coefficient is 1. I increase both x1 and x2 by 1 unit, which will have more effect on the target, x1 or x2? X1, right? Because x1's coefficient is bigger. Whichever factor's coefficient is bigger, for unit increase of that factor, y will respond more. Common sense, isn't it? So you can get feature importance, assuming you have scaled the data. That's a big assumption. Assuming you have scaled the data, all you have to do is compare the coefficients. When you compare the coefficients, let us look at the regression model's coefficients. Intercept is 3, which we can ignore. Slopes are, these are the coefficients. Coefficients of what? Coefficients of these predictors. So what I do here is, I just collate this. This belongs to horsepower. Second one belongs to weight. Third one belongs to this. I just collate it, and then I create a map. I create a hash map, and also I standardize. Like if I'm looking at percentage relevance, I have to add up all of those coefficients and divide each one by that, so that everything is on a scale of 1 to 100. So then what I find this is that the weight matters. 35% of the feature importance goes to weight. The lesson is, if you want high mileage, don't drive heavy cars, isn't it? Right. So go ahead.
So when you try to find the relative importance of a feature, what do you do with the constant? Just dropping it.
Yeah, the beta naught doesn't matter. Intercept doesn't matter.
You're not giving that
any kind of relevance. Yeah. So that is it. So this is it. You say a pi is 100 large. How much does each of the factors matter in that? And so weight, of course, don't drive heavy cars. So can I ask you this question? This is telling you that weight matters, and weight matters quite negatively. The more the heavier the car, the less the mileage. So therefore, should you start driving very light cars?
There's a safety factor there.
Exactly. There's a safety factor there. Because if you drive very light cars, or in the asymptotic limit, you start driving a motorcycle, which is very light, what happens? You become basically spare body parts, right? So, I mean, putting it harshly, but yeah. So in other words, miles per gallon is the only thing you ever optimize on, but in this problem, yes, right? So remember that everything has to be taken in perspective, of course. Perspective matters. So weight of the car. So for example, in my case, I tend to be environmentally very conscious, or I hope, well, I suppose we all believe we are environmentally very conscious, but then somebody looks at us objectively and says, you're not. I try to do my little bit. I'm a vegetarian. The biggest source of greenhouse gases seems to be the meat and fish industry. So I tend to be vegetarian. I don't go on expensive vacations, flying aeroplane flights long distance. The only flights I take are business related flights. My work requires me to fly, and whatever other means I can. But there is one place where I don't actually, I look like an eco-terrorist. And that is in the car I drive. As a physicist, I know that when an accident happens and somebody hits you at high speed, weight works in your favor, right? The momentum, mass times velocity. So if you are in a big vehicle, heavy vehicle, it will absorb more. And this literally happened. Some of you may remember, those of you have been with me. I used to drive this big car, big Infinity, a 5,000-6,000 pound Infinity. My life literally got saved. In my entire life, I'm a very cautious driver, I'm happy to say. I've never had an accident, and I've been driving since the age of 12. Right? I used to drive my mother's car. Since 12 or 13, I got behind the wheels in India and started driving. I've never had an accident, so I was very, very cautious. My colleagues used to say, when we would go out to lunch to a restaurant, people wouldn't want to car ride with me sometimes when I was because they would feel that they would reach last if they went with me. So I was very cautious. But then I had an accident. There was a police chase or something happening. There was a guy who was running away with a stolen car. And I was crossing over a highway, overpass, and this guy took an exit from the highway at full speed at 65, 70 miles, 50, 60 miles an hour. And he tried to, at the traffic light, right at the exit, he tried to make a turn, and I was coming literally like this, and he completely T-boned me, my car. He hit my car head on at 50, 60 miles an hour. And his car took such a hit, it spun and hit my car, and again spun and hit my car, twice or thrice. Right? And obviously, before I could even react, because I was happily going in my lane, looking at the traffic ahead, I had the traffic light and going through, and this car just escaped. And he went out of control because it was a police chase. He came and hit my car, and that car got, it was some Lexus, it got completely smashed. And the car spun a few times and stopped in the road. The guy was, it took him a while to regain consciousness. He got, and he ran away actually, ran away. What I found out is not only did he run away, once he gained consciousness, within 5 minutes, he carjacked another car and stole another car and escaped. By the time the police could chase him down, right, and really capture him, I don't know how he did it, but he managed to escape by stealing another car within 3-4 minutes after that, right? But it was the only accident I was in. But imagine being hit straight on your driver's side, on your door, and 2-3 times, you know, the car spinning and hitting you. I would not be alive here today and talking to you guys if I was not sitting in a heavy car. That's the first thing that came to my mind. It was a big Infinity, right? The biggest one, the QX80. Right? Well, in those days, it used to be called QX56. So big, heavy car. I still hold on to that car, even though it's old and it's battered up. And I like to drive it simply because it saved my life. Right? Literally saved my life. And I keep thinking as a physicist that you need to be in a heavy car. It doesn't make sense to optimize on that. And this was one occasion which literally happened. And prove the point. Anyway, so be it. So weight is most important. Horsepower, don't buy high horsepower cars because that will kill you. Actually, if you really think about it environmentally, what you should buy is big heavy car with not a very powerful engine, which picks up speed slowly, but then you'll be at risk when you merge on the highway, right? Anyway, there are many considerations. What I tend to do is have heavy cars which have high horsepower. So in matters of car, I'm an eco-terrorist.
So you mean to say Teslas are not worth buying in terms of weight and safety?
See, here's the thing.
So,
I'm on the fence with Tesla. I'm told those are heavy cars and they obviously give you extremely good mileage. The reason I've been on the fence with them is the software glitches. My friend went to a restaurant at night, and when he came back to return home, he found he couldn't get back into his car because there was a software glitch that has locked him out of his car.
Uh-oh.
Right. No, so I'm waiting for the technology to mature. It's an amazing car, but it has glitches.
so as if the Model X is pretty heavy. So about 2 weeks, 2 months back, Jay was driving the car and somebody came from back and they hit like a 65, 75 miles per hour. And the car essentially didn't move at all. And the only damage you can see in the bump in the back, of course, they're charging a lot of money to fix it because of the software and technology. But if you see the physical damage, the appearance, it looks very little.
Very little. Yeah, I'm on the fence. See, my time is over. I'm getting old now. My fascination with cars is more or less fading out. It's my kids' time now. My elder daughter, who just got a job in Snap, she has been toying with the idea of getting a Tesla. Right? She always wanted to get a Tesla with her first salary. So who knows? So there will be a Tesla in our family soon.
Nice.
We'll see. It's a lovely car. I mean, I'm very tempted. It's completely software driven. We teach machine learning. That car has tons of machine learning in it, AI in it. I would love to get it. I was just waiting for the glitches to go. So here we go. This is true for linear regression, but there is a technique called shapely values that I would say. It's the last topic of today. I'll talk about. There was a great mathematician. I think he's still alive or not. I think he may be alive. Shapley. Have you guys seen this movie, A Beautiful Mind?
Yeah.
John Nash.
Yeah.
John Nash's friend and colleague, Shapley. He got the Nobel Prize for answering one important question. He wrote a very simple equation, which when you see it on paper, you say, well, it's obvious almost, right? But he wrote that. It was game theory. John Nash, as you know, did game theory of the Nash equilibrium points. Excellent, Premjit. You know your game theory, right? So did you read the book also, or did you just see the movie?
I haven't read the book.
You haven't? Oh, the book is far superior to the movie. Movie doesn't do justice to the book. And John Nash used to actually live close to the Princeton railway station. And I am pretty sure, I'm not 100% sure, I'm pretty sure I've sat through his actual lecture at a time where I didn't know that he was such a great man. Right? Long, long ago, it's ancient history, but I may be wrong, I don't know. What Shapley answered the question was, suppose, imagine a team player. When you play a cooperative game, as opposed to a zero-sum game, a zero-sum game is chess, right? The only way one side can win is if the other side loses. The two don't cooperate and try to win together. You see that, right? Chess inherently is a zero-sum game. One guy will win and one guy will lose. Those are called zero-sum games. But then there are games like, let's say cricket or team sports. In any team sport, let's say cricket, which is most familiar to this audience here, what happens? All of the players, they need to work together to win. Otherwise, the other side will win. Isn't it? So it's a collaborative sport. It's still a zero-sum game between the teams, but within the team, there has to be a strong collaboration. It is a cooperative gaming. In such a situation, suppose the outcome is positive. You win. Now the question is, suppose I have a pot of gold. What is the fair distribution of that money? How would I spread it? Or how would I reward people based on their actual contribution to the winning? Now, you cannot just say the captain should get more or the leader should get more. So how do you determine the fair value of it? And there is a way of doing that. And I can go into that, but the simplest idea is that create teams or sub-teams. Okay, one naive way, which is not Shapely, let's call it baby Shapely. It's simply take a game, take a team in which this guy is there and this guy is not there. A team member is there and that team member is not there. And then see what is the outcome and see how much improvement in the outcome there is because of this team member. Are we together? Because of this team member, how much of an improvement in outcome was there? Right? But then you can say, well, you know what? There's a problem with this. This team member didn't make much of an improvement because there was exactly another person like him. Right? So took over. Now what happens? If you take both of those out and have a team without both of those and with both of them, then what happens? The difference is substantial. So you can say that half of the difference we can assign to each of the two, right? So this is it. Shapely, what it does is, now continuing that idea forward, what it does is it creates all sorts of teams with or without this person there and looks at the average difference between all of them. And that is the contribution of this person. And then you do it for all the other players. So those contribution values are called Shapely values. And for this particular idea, Shapely actually got the Nobel Prize, right? Simple but profound idea because it addressed a key question in economics. How much is a person worth being rewarded for contribution? Now, what has that to do with machine learning? It turns out, as people are beginning to realize, game theory has a lot to contribute to machine learning. People are only beginning to realize that. They have realized it for some time, but more and more they're realizing that. So here, suppose we do this. You have a model which is effective. You got to an effective model, right? The effective model has all sorts of predictors there. How important was this predictor in getting an effective model, in getting a good prediction? That matters, right? And you can talk of the relative importance. How much contribution did each of the predictors bring? Because that is literally the feature importance or the predictor importance. Do you agree with that? Right? And so you can treat it as a game. You can say that if you treat the predictors as a team and the game being make an effective prediction, how much did each team member, namely each predictor or feature, contribute to the outcome? That is its features or predictors importance. So that is what is the Shapely value. In Python, there is a package called SHAP, which helps you do that. It's a lovely package that is very deep and it has many things in it. We will gradually come to that, but for now, we'll start with something simple.
Question before we get to the interpretation. So to do Shapely interpretation of which features contributing more, one has to necessarily make the assumption that the model that you're starting with has just the right set of features which gives it the maximum in terms of the R-square.
Not necessarily. All it means is that there may be still an unknown feature, which is even more important. But it is relative importance of the features that you have built. If you're happy with this predicted model, you consider this is the best I could do, given the data that I'm available. The question still remains, what is the relative feature importance?
So then if you stretch that argument, you would say the ones that we removed for collinearity, you will still put them back in when we
Yes. So what happens is that collinearity argument, actually, this is one of the reasons why when you do Shapely, you have to be careful because if you remove predictor, whatever contribution you gave to this, suppose this was one amongst three, you have to remember that this is 1/3 between those three predictors. You have to remember to do that. right? So in other words, if you say, for example, weight is most important, so you must remember that not only weight, acceleration is most, not acceleration, but displacement is most important, right? And what was the other factor that we removed? Because of weight, we removed two other factors. Where are my factors that we removed? Cylinders. So if weight is most important, then displacement is also most important, and cylinders is also most important. So you have to remember to bring back that interpretation. Right, that is it. And now what happens is, this is peculiar to linear regression models when you go to linear models, but when you go to non-linear models, you never throw away the collinearity doesn't exist, so you don't throw away correlated features, right? So this is the interpretation of it. So now when you use the SHAP package, you will see that sure enough, weight is number 1, horsepower is number 2, year is number 3, acceleration is 4. You see that, right? And you see it here, weight, horsepower, year, acceleration. You see the same order, right? So for linear model, the advantage is, and it's one of the things not many people realize, that if your data is scaled, the easiest way to see feature importance is literally look at the coefficient. It is obvious from the geometry of it, isn't it?
So again, one more question there.
Yeah.
So in the previous one, when we were just looking at the coefficients, we had to make sure that we had normalized each of those variables.
Yes, you must have.
But for SHAP, is it necessary, or would SHAP package take care of all that?
See, here is a basic rule. To not normalize the data, not standardize the data, is almost like waking up and going to breakfast without brushing your teeth. Right? You should always do it. It's not worth thinking, in this situation, could I have not standardized the data? You don't. You wake up in the morning and you standardize the data. Then you continue on to anything else. Right? So just make it a habit. Always standardize the data. Linear model is the only model that sort of doesn't fall apart if you forget to standardize. But even then, the gradient descent gets adversely affected. Right? But so just always standardize the data. Consider it to be good hygiene. Wake up in the morning, standardize the data, and then brush your teeth. Right? Sort of like that. Then there is something called partial dependency plot. What it means is that, so if you look at the weight and the miles per gallon, you're saying if all other factors were the same. You know, people in economics use this language. How much does, for example, if government issues a lot of money, how much does that affect inflation? All other factors being the same. People are still manufacturing what they are manufacturing. So it is the partial dependence or partial relevance. So that is partial dependence. How much does the miles per gallon depend on weight? When you look at it, quite a bit. By the way, it's not weight. It is log miles per gallon and log weight. Remember, that has a linear relationship. Quite a bit. How much does the log miles per gallon depend on log horsepower? Quite a bit, but not as much. You notice that this is steeper than this, or little bit steeper. This is little, leftmost is little steeper than the middle one, and all of them are far more steep than the acceleration one. Acceleration doesn't matter that much, right? And you can see it in the feature importances also. Weight, horsepower, they basically kill compared to acceleration, which has only a 6% influence, right? And so these are partial dependency plots. So guys, what I'm saying, this is a known data set, of course. Many people have analyzed the Kaggle notebooks, this notebook, that notebook, medium notebooks, etc. Generally, they all do a good job. But I'm trying to raise you, I believe, to a higher bar, to make you stronger than that, to make you at a place at which you do a rigorous and careful analysis of the data and build models very, very carefully. I want you to, it's a long analysis of a simple data set, but I want you to get used to this analysis, right? Thorough, careful, methodical analysis of the data, and get into the habit of doing such careful analysis, right? Don't be like one of these people who just does a small analysis and promptly writes a medium, which is good. You write a Medium article to say, yay, I learned how to do analysis. So it will be useful to somebody. They too are contributing value, but you contribute more value to society and to the field if you submit a notebook in which you have done a very thorough and careful analysis of data. Are we together? Make it a habit, because when you do very methodical and careful analysis of data, you are much more likely to hit upon a breakthrough in case a breakthrough is sitting waiting to be discovered in the data. Right? Do that. And remember, all breakthroughs come from the data eventually. So with that thing, it's 5:40. It's been a long day, guys. I will let you go, let you folks go. I was going to cover two more things. I suppose I'm ambitious. I'll give you an idea. Go read this. One of them is the California housing data set. In California, everybody seems to be worried about their home values. People who have home keep hoping it goes up. People who don't have homes or in apartment keep hoping it crashes. Right? So, well, this is it. So the same analysis I've done more or less along the same lines methodically, except that because it's geographical data, I plotted it out. We'll talk about it next time. But if you take some time to study it, and my notes are here, perhaps we can move faster, right? And you will see that it is along very similar lines. There is something new here, and I've used only linear regression. Later on to the same data sets, we'll apply nonlinear techniques, we'll apply gradient boosting, we'll apply random forest, we'll apply support vector machines and whatnot, and we'll see how they respond to more sophisticated models. Right? But this is it. Please do study this on your own. The other thing, the topic that seems to be missed continuously is the topic of tidy data. So I'm thinking, because these topics are overflowing and now we are getting into classifiers, we may not get time. I will hijack some of these paper reading sessions instead to talk about each of these topics independently. They are of value to even a general audience. So if other people from outside join, even better. We'll give one session to tidy data, one session to, well, California housing I'll do, it's important, so I'll do it in the next session. But one session to this collinearity, right, on Tuesday. So we'll take those times to talk about those topics. But with all of this, at this point, I would like to end by saying, guys, if you have been studying the lab, if you have been playing with data, if you have been doing your homework, by now, you should feel reasonably familiar with regression. I wouldn't say you mastered it. Learning is cyclic. The first time you learn something, the best you can hope for is you understood and is beginning to feel familiar. The second time comes deeper comprehension, and fluency comes in a few cycles. Learning, if we have learned anything about learning is cyclical. You have to keep revisiting the same thing, and every time you revisit, it gets deeper. It's one reason I have invited people to repeat this class over and over again, free of cost. So that now you don't have to necessarily repeat all the way, but as you learn this, keep seeing if you can get opportunity to keep cycling through what we have learned. Go back to the videos, take the quizzes, do the projects, do the labs. Now, as you do the homework, guys, please submit it, or at least do it. If nothing else, do it. Because unless you do it yourself, you will never build confidence. Right here, I noticed that not many of you, some of you have been doing it. Some of you also have not been doing your homework. Do it. I know we are all busy. We are all adults. We are professionals. We never get time. The time is the most precious thing in our life. But if you, to the extent that you have the aspiration to master all this, that will only happen if you give it the commitment of time. Please do give it. I will end with that. Thank you, guys. And thank you, Kyle, for staying up so late into the night, practically. It must be 6 in the morning by now.
She's amazing.
Yeah.
Yes. Thank you.
Nice Moringa notebook too.
One second. Kate, please go ahead.
Oh, her Moringa notebook was really good too.
Yes, her Moringa notebook was amazing. So I would like somebody else to present. Sanjeev, let's have you present your project next time.
Yeah, I will do that, Asif. Yep.
Definitely. Yeah. Go ahead, Anil. It's already there on the web page.
No, it's But we are not referring it to the.
Oh, to the URL. Just to the local one. Huh? Let me see. I'll fix that. I'll fix and post it again.
And so in the auto one I was running, you can't include the power transform in the support library.
Power transform. No, oh, I have to update the support vectors common. Okay, I'll fix all of those. Huh? I will do that. In fact, I should do it right now. I can do it. Let me.
Also the format of the auto one I think is so the auto one or format is
Okay. Why don't I come and check? 1 second. Huh? By the way, guys, are you finding these libraries useful? I mean, not the libraries, the notebooks.
Notebooks are great.
Notebooks are useful. Good. So,
The notebooks are very helpful. You can read it like a book. At the same time, there's code to look at.
yeah. They are literally part of the book I'm writing.
I haven't done justice to it, so I need to do justice.
Where is it? Can you please do that again?
right
Download it.
into
Yeah.
the support vector.
Yeah.
And the file format, the auto.
Oh, auto. Let me do that.
The one that was the-
Oh, so let me update that auto. The auto is pointing to the remote file, no? Yeah, it is pointing to the
file-
California. California is a
No,
problem.
that's this problem, but the format of the file also.
No, it shouldn't be a problem.
um,
Just get the support vectors library and after that run it. I'll come and sit with you and make sure it's all working.
yeah.
Housing is the problem. Housing I have to upload.
Yeah, auto notebook. Auto notebook. It basically said save link here. So basically it's just I think the top part of it gets messed up, right?
Yeah. I will fix it.